Somewhere in the quiet stillness of the night sky, a secret stirs. Among the thousands of stars that seem fixed and eternal, one hides a strange and explosive truth. It waits. It sleeps. And then, once every lifetime, it erupts like a cosmic phoenix, flooding the sky with brilliance before vanishing once again into silence. This isn't a myth. This is real. This is the story of T Coronae Borealis, a star that doesn't die, but reawakens. But before we continue, subscribe to the channel and like the video. Imagine being out beneath a clear night sky, far from city lights, scanning the stars overhead. The sky seems calm, ancient, unchanging. But then, suddenly, a star you've never seen before appears, a bright light that wasn't there the night before. It burns with a fierce glow, brighter than most around it. And then, just as mysteriously, it fades again over the weeks to come, retreating into invisibility for another generation. You just witnessed a rare phenomenon, the rebirth of a star. A re-eruption. A blaze in the sky that astronomers have come to know and fear as TCRB. This isn't a typical star. It doesn't shine steadily like our sun. It doesn't gradually swell into a red giant and fade into a white dwarf like most stars do. It lives a dual life, flickering between invisibility and outburst. For decades, it plays dead, a ghost among the stars. Then, without warning, it awakens in fury, releasing energy on a scale we can scarcely imagine. This explosion isn't its end, it's just another heartbeat in a long, violent rhythm. T Coronae Borealis belongs to a rare class of celestial objects known as recurrent novae. Most novae erupt once in recorded history and vanish forever. But TCRB returns. Predictably. Menacingly. Every 80 years or so, this system comes back to life, and the world watches. Its last eruption? 1946. Just after the close of World War II. The Earth was rebuilding, reshaping, rediscovering peace. And high above, hidden in the quiet reaches of Coronae Borealis, TCRB blazed like a flare in the night, announcing its return to those who were watching. Now, nearly 8 decades later, it's stirring again. But why does it do this? How can a star explode and survive, not just once, but again and again? What mechanism powers this cycle of destruction and rebirth? Is this star just repeating its cycle endlessly, or is it building towards something far more final? This is not a gentle story. This is the tale of a stellar predator and its prey. A binary system in which one dead star feeds off its living partner, until it erupts. And it will erupt again. Across Earth, astronomers are watching. Telescopes, ground-based and orbiting, are fixed on TCRB, measuring its every twitch, every flicker. And the anticipation is growing. Soon, this invisible point in the sky may become one of the brightest stars we see. A once-in-a-lifetime event. A cosmic signal fire. And we are here for it. So buckle in. This is not just about astronomy. It's about witnessing the sky change. About watching a cosmic cycle as old as time. It's about the thrill of knowing that something is out there, biding its time, ready to blaze again. This is the Blaze Star. And it's waking up. In the heart of the Coronae Borealis constellation lies a star system with a name that carries fire in its breath, T Coronae Borealis. But for those who know its story, that name is just the beginning. To skywatchers, it's been given a more poetic and ominous nickname, the Blaze Star. And that name isn't just for show. This is the star system that has, quite literally, burst into brilliance and then vanished from sight, not once, but twice in recorded history. And it's preparing to do so again. To the unaided eye, for most of the time, TCRB is utterly forgettable. It's a faint point of light, sitting at a quiet magnitude around 10, far too dim for the naked eye. For decades at a time, it's practically invisible without a telescope. But this obscurity is deceptive, because when it awakens, it does so with terrifying power. Within the span of a single night, TCRB can leap in brightness, suddenly outshining stars that had for years dominated its section of the sky. It becomes visible to millions, glowing with the intensity of a star that shouldn't even exist at that location. This violent transformation is what earned it the nickname. When it erupts, it doesn't just brighten, it blazes. It sets its small corner of the sky on fire, if only for a brief time. But perhaps the most intriguing thing about TCRB isn't its brightness, but its rhythm. Most novae, stars that undergo dramatic increases in brightness due to a violent release of energy, do so only once, at least in our recorded history. They flare up and disappear, never to be seen again. But TCRB defies that rule. It comes back. Like clockwork, it erupts approximately every 80 years. This behavior places it in one of the rarest classes of stellar objects we know, the recurrent nova. Only a handful of recurrent novae have ever been documented, and among them, T Coronae Borealis stands as one of the most famous. It's not just because of its brightness. It's not just the fact that it returns. It's the eerie feeling of inevitability. It's the tension of waiting. There's something haunting about a star that hides for generations, then unleashes a burst of energy with pinpoint reliability. It's like watching a volcano that erupts once in a human lifetime, knowing that the next blast could come at any moment, and this time, you're standing on the edge. This predictability isn't just dramatic, it's a gift. Astronomers don't often get warnings. Cosmic phenomena are usually random, unexpected, chaotic. But TCRB gives us time. It gives us a countdown. It gives us a rare opportunity to prepare every instrument, every telescope, every eye, and be ready for the show. But behind the nickname, behind the bursts of light, lies a deeper mystery. T Coronae Borealis is not a single star. It is a system, a binary system, and it is the hidden relationship between its two components that gives rise to its terrifying beauty. The blaze star isn't just flaring for attention. It's the visible tip of a dark, violent secret. A dance of death playing out across decades. A slow-motion cosmic theft. And to understand it fully, we must look deeper, not just into the star itself, but into the space between two stellar companions locked in an intimate, destructive orbit. High above Earth, nestled within the twisted arc of a faint northern constellation, lies the resting place of T Coronae Borealis. To find it, one must know where to look, because unlike the blazing giants of Orion or the sweeping spiral of the Milky Way's core, TCRB does not reveal itself easily. Most of the time, it's hidden in plain sight, sleeping amid a delicate crescent of stars that form the Corona Borealis, the northern crown. The Corona Borealis constellation itself is a subtle formation, shaped like a horseshoe or a tiara, a faint semicircle of stars tucked between two more famous constellations, Boötes the herdsman and Hercules the strongman. On a dark night, far from city lights, it can be seen arcing gently across the northern hemisphere's summer sky, especially prominent in June and July. It sits relatively high above the horizon for observers in the northern hemisphere, which makes it a seasonal favorite among amateur astronomers, not because it's flashy, but because it feels like a hidden gem. A crown of stars, quiet and graceful. Within this crown lies TCRB, but locating it isn't straightforward unless it's an eruption. Most of the time, it hides at magnitude +10, making it completely invisible to the naked eye. To find it in this dormant state, a telescope or high-powered binoculars are required, along with a star map or digital sky atlas to guide your search. You'll need to zoom in on the southeastern edge of the constellation, near the star Epsilon Coronae Borealis. Even then, what you'll see won't be striking. It will appear as just another dim speck, lost among the background stars. But this changes completely when TCRB erupts. During its historical outbursts, TCRB leapt to a magnitude of around +2, brighter than Polaris, and clearly visible even from light-polluted urban skies. In that moment, it becomes one of the brightest stars in the entire region, a light that hadn't been there the night before. If you were to glance toward Corona Borealis on such a night, even without knowing the coordinates or consulting a chart, you would notice it immediately. A new star. A ghost resurrected. A star that shouldn't be there, and yet is. When the next eruption occurs, it will likely be best viewed in the northern spring or summer, when Corona Borealis is high in the sky after midnight. From latitudes above the equator, it will hang above the horizon with elegance, a celestial crown glittering quietly, until the blazed star ignites again. modern skywatchers can also turn to technology for assistance. Apps like Stellarium or Sky Safari, when set to the right date and location, can pinpoint TCRB's exact coordinates, guiding telescopes to its location. Observatories around the world already have it locked in their crosshairs, but for amateurs hoping to witness the next event with their own eyes, the process is surprisingly simple. Wait for the flare, and then look toward the northern crown. Because when TCRB awakens, you won't need maps. You won't need coordinates. You'll just look up, and there it will be, blazing from a part of the sky you thought you already knew. In the deceptive quiet of space, many stars appear singular, solitary beacons shining alone in the vastness. But this is often an illusion. A significant fraction of stars in our universe are not alone, but part of intricate systems, binaries, trinaries, gravitational families of light and mass bound together by invisible threads. T Coronae Borealis is one such system. But unlike the gentle orbiting companions we find elsewhere, the relationship between the two stars that make up TCRB is far from harmonious. It is a relationship defined by hunger, tension, and destruction. The Blaze star is not one star. It is two, a binary system with a terrible secret. One, an old red giant nearing the end of its life, bloated and bleeding matter into the void. The other, a white dwarf, the dense, burned-out corpse of a once luminous star, now collapsed into an object no larger than Earth but more massive than our Sun. Together, they are locked in a cosmic waltz, their fates intertwined, their very survival linked to a process of slow and inevitable consumption. From a distance, they orbit one another like countless other binary pairs. But up close, the details are disturbing. The red giant, a swollen star many times the size of our Sun, has reached a stage in its life where its outer layers are no longer tightly held. Its surface is loose, extended, and unstable, like a balloon stretched too far. It expands and pulses, and as it does, it overflows its own gravitational boundary, a region known as its Roche lobe. The moment this boundary is breached, something dramatic happens. Matter begins to flow from the red giant into the gravitational embrace of its tiny but powerful companion. The white dwarf, though small, is incomprehensibly dense. Imagine compressing the entire mass of the Sun into a sphere about the size of Earth. That's the scale we're dealing with. This dead star has no fuel of its own left to burn. It no longer fuses hydrogen in its core. But it still possesses gravity, powerful gravity. And with that comes a kind of vampiric appetite. As the red giant spills its material, primarily hydrogen, the white dwarf greedily gathers it, pulling it toward itself in a process known as accretion. This is where the story takes its darker turn. Accretion is not a peaceful process. The material stolen from the red giant doesn't simply disappear into the white dwarf. Instead, it forms a swirling, spiraling disk of gas, an accretion disk, heating up as it spirals closer and closer to the dwarf's surface. This disk glows with energy, and in some systems, it's enough to be seen with our instruments even when the system is otherwise quiet. In TCRB, this disk is the quiet forge where future violence is built. Over years and decades, more and more hydrogen piles up on the surface of the white dwarf, clinging there due to the star's crushing gravity, but not fusing. Not yet. The binary system continues like this for decades. Matter flows. The disk grows. Hydrogen accumulates. And the white dwarf waits. Until, finally, it reaches a tipping point. As the hydrogen layer thickens and compresses, the pressure and temperature on the surface of the white dwarf rise to critical levels. And when the conditions are just right, something extraordinary happens. Thermonuclear fusion ignites in a runaway reaction. But unlike the steady fusion that powers stars like our Sun, this is uncontrolled, a flash fire erupting across the dwarf's surface, releasing a tremendous amount of energy in a matter of hours or days. The entire outer layer of hydrogen detonates outward into space. This is what we see from Earth as the nova, the sudden brightening, the blaze that gives TCRB its name. This eruption is not the death of the system. Unlike a supernova, which marks the end of a star's life, a nova is more like a violent reset. The white dwarf survives. The red giant survives. The cycle continues. The red giant continues donating material. The white dwarf continues building its deadly layer of hydrogen. And after enough time, decades, maybe 80 years or more, it happens again. This binary system, then, is not a peaceful partnership. It is a system governed by gravity, time, and destruction. One star is dying, slowly losing its outer envelope to space. The other is already dead, yet stealing life from its partner in order to momentarily flare back into brilliance. They are locked together in an endless act of stellar cannibalism. And every few generations, humanity looks up and sees the result. There's something unsettling about this, isn't there? We often think of stars as distant, impersonal entities, but this is a system of need and violence, of slow inevitability. TCRB is like a slow fuse attached to a celestial bomb. The two stars are locked in a fatal embrace, and with every moment, the white dwarf grows a little closer to instability, a little heavier, a little more dangerous. And that raises a chilling possibility. What if one day, the white dwarf goes too far? The red giant in the T Coronae Borealis system is the silent architect of every explosion, the quiet donor in this cosmic transaction of mass and violence. If the white dwarf is the match that strikes the flame, the red giant is the leaking tank of gas feeding the fire. Its role is less dramatic at a glance, but no less critical. In fact, without it, there would be no blaze at all, no eruption, no spectacle, no TCRB as we know it. This red giant is a star in its twilight years, old by stellar standards, evolved, and swollen far beyond its former size. Once it was a main sequence star, perhaps not too unlike our Sun. But as it exhausted the hydrogen fuel at its core, it began to change. The core contracted, the outer layers expanded, and the star grew in size dramatically. It is now hundreds of times larger than it once was, with a cool, ruddy glow that marks its classification as an M-type red giant. And that growth, that bloating, is precisely what makes it dangerous. In isolated stars, red giants eventually shed their outer layers in slow stellar winds, drifting off into space to form planetary nebulae, leaving behind a white dwarf core. But in a binary system like TCRB, something else happens. The red giant's expansion causes it to fill a critical region of space, its Roche lobe. This is the zone within which the star's gravity dominates, holding its own gas close. But once the outer layers swell beyond that boundary, the material is no longer gravitationally bound to the red giant alone. Instead, it begins to drift, not aimlessly into space, but toward the white dwarf companion. It is here that the true drama unfolds. Gas from the red giant begins to stream through the inner Lagrangian point, the gravitational gateway between the two stars, forming a stream of hydrogen-rich matter that flows directly into the white dwarf's gravitational well. This is not a violent ripping apart, at least not visibly. It's a steady, silent siphoning. A transfer of stellar essence from one body to another. Over time, this flow becomes the foundation of the accretion disk, a swirling, spiraling disk of gas that forms around the white dwarf. The material doesn't fall directly onto the compact star. Instead, conservation of angular momentum forces it into a disk, which heats up as it compresses. In other recurrent novae, this accretion disk often emits X-rays and ultraviolet light, betraying its presence even when the system is not in outburst. In TCRB, the red giant's wind and direct transfer contribute significantly to this ongoing buildup. But this process is not uniform or constant. The red giant is a variable star, meaning its brightness, and thus its outer envelope, changes over time. It pulsates, its size and temperature subtly shifting in a slow rhythm. These changes can affect the rate of mass transfer, causing periods of increased or decreased accretion onto the white dwarf. This variability is one of the reasons predicting the exact timing of the nova event is so difficult. A slightly faster flow might push the system toward eruption sooner. A slightly slower one might delay it by years. There is another curious wrinkle. The red giant is not entirely passive in this relationship. Observations suggest that its atmosphere is being heated by the proximity of the white dwarf and the accretion disk. This heating can trigger stellar activity, flares, enhanced wind, and possibly even changes in its envelope, which further complicate the already dynamic exchange between the two stars. The red giant, in this sense, is not just a fuel source. It is a changing, reacting, living participant in a delicate, explosive balance. Every atom that leaves the red giant's surface is a step toward ignition. Every wisp of hydrogen that crosses into the accretion disk is a countdown. The red giant is shedding mass, losing part of itself, not in a chaotic burst but in a long, drawn-out donation. It is being consumed, atom by atom, not for nothing, but to fuel a moment of extraordinary brightness that will one day blaze across the heavens. And in the aftermath of that blaze, once the white dwarf has expelled the unburned remnants of the explosion, the cycle begins again. The red giant continues to bleed. The white dwarf continues to feed. And all the while, the universe watches in quiet anticipation. What's especially haunting is that this red giant's life is being extended by its death. Were it not in a binary, its evolution would follow a different path, perhaps quieter, slower. But here, caught in gravitational intimacy with a dead star, its outer layers are being stripped before they're ready, accelerating a transformation it cannot control. In the end, it too will become a white dwarf, long after it has fed the fury of TCRB for decades or centuries. This system is a perfect example of stellar codependence, not romantic, but fatal. The red giant cannot stop feeding, and the white dwarf cannot stop devouring. Their futures are entwined, and their actions today determine the fate of the system tomorrow. They orbit a shared center of mass, but metaphorically, they orbit something deeper, a destiny either of them can escape. The red giant's role is that of a giver, perhaps unwilling, perhaps unaware. It plays the part of sustainer, offering its body for the spectacle to come. Without its overflowing outer layers, without the instability that comes with its age and size, there would be no nova. The blaze would never rise. The sky would never change. But because of it, because of this slow, persistent act of stellar surrender, we are gifted with one of the rarest sights in the cosmos, a star that reawakens. A system that explodes, not once, but again and again. And a future that is as uncertain as it is magnificent. While the red giant offers its mass to the void, quietly spilling its atmosphere into the gravitational domain of its companion, the real force behind the cosmic fireworks of T Coronae Borealis is the white dwarf, a remnant of a star long dead, but far from peaceful. Though it may seem inert to the naked eye, this stellar corpse is anything but dormant. It is the engine of the eruption, the spark behind the blaze, and perhaps one of the most dangerous objects in the night sky. The white dwarf in the TCRB system is an incredibly compact object. Once a star not unlike our own Sun, it burned through its fuel billions of years ago, shed its outer layers, and collapsed into itself under the immense pull of its own gravity. What remained was a sphere about the size of Earth, but with a mass nearing that of the Sun. That's equivalent to packing the mass of 1,000,000 Earths into a single planet-sized object. The result is a star so dense that a teaspoon of its material would weigh as much as an SUV. Its gravity is extreme. Its surface conditions are unimaginable. And in the TCRB system, it is hungry. This hunger manifests not as some explosive burst of consumption, but as a silent, steady accumulation of mass. As the red giant overflows, its hydrogen-rich gas is drawn into the gravitational field of the white dwarf. But it doesn't fall straight in. Instead, the gas swirls into an accretion disk, a flat, spiraling structure of plasma that forms around the dwarf like a whirlpool of starlight. Here, friction heats the gas to extreme temperatures, emitting ultraviolet light and X-rays. The disk can be faintly visible in high-energy wavelengths, even when the system is otherwise quiescent. As more and more gas accumulates, it gradually spirals inward from the disk and settles on the surface of the white dwarf. There, it forms a growing shell of hydrogen, a tenuous, unstable skin that doesn't sink into the core, but clings to the surface under intense gravitational pressure. The white dwarf itself doesn't ignite this hydrogen right away. In fact, it holds it, compressing it more and more, until the temperature and pressure reach a catastrophic threshold. Here lies the secret to the explosion. Hydrogen fusion, the same process that powers the cores of main-sequence stars, requires incredibly high pressures and temperatures. On the surface of a white dwarf, with gravity about 100,000 times that of Earth, those conditions are achieved not by internal pressure, but by sheer gravitational compression. As the layer of hydrogen thickens, its lower levels become so hot and dense that the atoms begin to undergo thermonuclear fusion. But because the surface is so thin, and because the white dwarf has no way of regulating this energy release, no convection currents like in a normal star, the process spirals out of control. A thermonuclear runaway begins. In the blink of an eye, the accumulated hydrogen detonates. Not in the core, but in a shell above the surface, a fiery flash that engulfs the star's exterior in searing light and blasts the upper layers of gas outward into space. The energy released is immense, the brightness of hundreds of thousands of suns, all pouring forth from a single point. This is what we witness as a nova. In TCRB, this explosion propels the star's brightness from a feeble magnitude 10 to around magnitude 2, a jump of 8 magnitudes, or about 1,500 times brighter than before. But make no mistake, this is not a supernova. The white dwarf survives the blast. The eruption is not its death, but a violent shedding of its excess. It expels the hydrogen shell, radiates away the energy, and then begins again, waiting, accumulating, compressing. The hunger does not end. It is only momentarily satisfied. What's remarkable about TCRB is the speed of this transformation. Most stars evolve over millions or billions of years. TCRB changes in days. The eruption begins suddenly, reaches peak brightness within a day or two, and slowly fades over the course of weeks to months. Then it goes silent. The white dwarf returns to its accretion phase, as if nothing had happened. But under the surface, the cycle has already restarted. What makes this system even more astonishing is the delicate balance involved. The white dwarf must accumulate hydrogen slowly, not too fast, or the system could become unstable in other ways. And not too slowly, or the eruption might never reach threshold. It must hold on to the gas just long enough for the fusion trigger to be absolute. If the pressure is too low, the hydrogen burns quietly. If it's too high, it explodes catastrophically. TCRB has perfected this balance, again and again. But the danger doesn't end there. Every time the white dwarf erupts, it loses a bit of the accreted hydrogen. But not all of it. Some of the material may sink into the dwarf's surface, adding permanently to its mass. And here's the cosmic catch. If the white dwarf continues to grow in mass over many cycles, it edges ever closer to a deadly limit, the Chandrasekhar limit, roughly 1.4 times the mass of the Sun. If the dwarf crosses this boundary, the balance of forces inside it breaks. It can no longer support its own mass. And in that case, the eruption is not a nova. It is a supernova, a type I, a final, irreversible explosion that annihilates the star entirely. For now, TCRB has not reached that limit. But astronomers are watching. Each eruption is a reminder of what could come. Each cycle is a step closer. And while this white dwarf survives its blaze for now, one day, if the conditions are just right, if the red giant feeds too much, or the dwarf holds on too tightly, it may go beyond what the laws of physics can contain. Until then, it waits. Gathering fuel. Compressing matter. Growing heavier. Growing hotter. Like a ticking time bomb with a cosmic fuse, the white dwarf sits in silence, absorbing the life of its companion, storing the energy of its eventual rebirth. And when the next moment comes, when it has taken just enough, it will ignite again. Not in death, but in fire. Not in silence, but in a blaze the whole world can see. When most people hear the word nova, they think of a star exploding, a single, powerful, irreversible burst that marks the end of a stellar life. But this isn't quite accurate. A nova is not the death of a star, but a dramatic episode in a star's life, an eruption that flares and then fades, leaving the central system intact. And for the vast majority of novae we've observed in the galaxy, this is a once-in-recorded history event. A sudden blaze in the sky, a momentary spotlight, and then nothing. Silence. Permanence. The star might still exist, but the show is over. But every so often, something stranger occurs. Some stars don't erupt just once. They erupt again. and again, and again. These are the rare few known as recurrent novae, and T Coronae Borealis is among the most intriguing and famous of them. To understand why this matters, we need to first grasp what defines a typical nova. In almost all cases, a nova involves a binary system, as we've seen with TCRB, a white dwarf pulling matter from a companion star. The white dwarf collects hydrogen on its surface until the pressure and temperature are high enough to ignite thermonuclear fusion in a runaway reaction. This leads to a violent explosion on the surface, a nova. The result is a sudden spike in brightness, a shedding of the outer hydrogen shell, and then a gradual return to quiescence. Now here's the key: in most novae, this cycle happens so slowly that it may never repeat within a human lifetime, or even within recorded human history. The accumulation of matter takes tens of thousands, or even millions of years. The conditions needed to reach critical fusion temperatures simply take too long to recur. Once we've seen one, we may never see it happen again, at least not from Earth. But a recurrent nova breaks that rule. Recurrent novae are special because their eruption cycles are measured not in millennia, but in decades. That alone makes them exceptionally rare. Out of the hundreds of classical novae discovered over the past few centuries, only about a dozen have been confidently identified as recurrent. And of those, very few display such dramatic and predictable behavior as TCRB. In fact, only a handful have confirmed eruption intervals short enough to observe 2 or more outbursts within the same human lifetime. This leads to a fascinating question: what makes a recurrent nova different? Why can some white dwarfs erupt over and over again, while others take eons? The answer lies in a precise blend of mass, accretion rate, and binary dynamics. Firstly, the white dwarf must be very massive, close to the Chandrasekhar limit, the point at which its gravity is so intense that even a small amount of added mass could trigger catastrophic instability. The higher the mass of the white dwarf, the less material it needs on its surface to trigger runaway fusion. This shortens the time between eruptions. In essence, a more massive white dwarf is more sensitive to incoming hydrogen and will erupt more readily. Secondly, the rate at which the white dwarf accretes matter from its companion must be unusually high. The red giant in the TCRB system plays a critical role here. Because its outer layers are so bloated and unstable, and because it overflows its Roche lobe, the flow of material into the white dwarf is not just a trickle, it's a steady stream. That means the hydrogen layer builds up quickly. In TCRB's case, it takes roughly 80 years to reach the critical threshold. In other recurrent novae, this period may be as short as 20 years. And thirdly, the structure of the binary system, especially the distance between the stars and the size of their Roche lobes, must allow for continuous, efficient transfer of mass. If the stars are too far apart, the material may never reach the white dwarf in sufficient quantities. Too close, and the system might destabilize or merge. TCRB exists in this rare sweet spot, close enough to allow ongoing accretion, stable enough to repeat its cycle, massive enough to ignite its surface hydrogen, and distant enough that each eruption doesn't destroy the entire structure. Another feature of recurrent novae is their light curve, the pattern of brightness over time during an eruption. In classical novae, the fade from peak brightness can take months, or even years. In recurrent novae like TCRB, the decline is usually rapid. The system might reach peak brightness in just a day or two, and then fade back into obscurity over a few weeks. This rapid rise and fall is another clue that the white dwarf is already near maximum mass, and thus needs only a thin layer of hydrogen to detonate. But this rarity comes with a tension. The very conditions that allow a nova to recur also make it inherently unstable over the long term. Every time the white dwarf accumulates more hydrogen, there is a risk that not all of it will be ejected during the explosion. If even a small fraction is retained, the white dwarf gains mass, and creeps ever closer to the Chandrasekhar limit. That's why astronomers watch recurrent novae so carefully. They're not just marvels of astrophysics. They are potential Type I supernova progenitors, candidates for one of the most powerful and destructive events in the universe. TCRB has now erupted at least twice in recorded history, in 1866 and 1946. Each time, It followed the same pattern: a sudden jump in brightness, a spectacular flare, and a return to dormancy. Now, more than 75 years later, the clock ticks toward a possible third act. If it erupts again within this decade, it will further solidify its reputation as one of the most reliable recurrent novae ever discovered. To witness a recurrent nova in action is to watch a system defy cosmic timescales. It's like seeing a volcano that erupts on cue, every few decades, a rare phenomenon in a universe that prefers chaos and randomness. TCRB is a lighthouse in this darkness, a rare marker of celestial repetition. But repetition does not mean safety. It only means we know the pattern, and that someday, the pattern may end with a final, permanent flash. Until then, it remains a timepiece. A stellar metronome. A fire waiting to be lit once more. In the vastness of space, most celestial events are governed by timescales too vast for human comprehension. Stars take billions of years to evolve, galaxies collide over hundreds of millions, and black holes can lie dormant for eons before feeding again. So when we come across an object like T Coronae Borealis, a system that erupts with near-clockwork precision every 80 years, we are faced with a remarkable anomaly, a cycle of cataclysm that syncs with human generations. A pattern just slow enough to be missed by most in a single lifetime, but fast enough that records and observations can link one explosion to the next. This is the nova cycle, and at its core lies an explosive balance of pressure, gravity, mass, and time. This cycle begins quietly. After an eruption, the system cools. The white dwarf has expelled the accumulated hydrogen in a brilliant thermonuclear outburst, flaring to thousands of times its normal luminosity. The accretion disk is disrupted. The red giant, its outer layers stirred but not consumed, continues orbiting, unchanged in its devotion, or perhaps its imprisonment. Then, the recovery begins. Material from the red giant starts to flow again. Hydrogen-rich gas, driven by gravitational imbalance and the red giant's own instability, begins to accumulate around the white dwarf. The accretion disk reforms, swirling in tighter and tighter spirals, funneling matter onto the surface of the dwarf. This is not a chaotic, sudden event. It's a steady drizzle of fuel. Drop by drop, gram by gram, the hydrogen piles up. This part of the cycle, the quiet accumulation, takes decades. The accretion rate of TCRB is relatively high for such systems, and yet even so, the white dwarf must patiently gather the equivalent of several trillion tons of hydrogen before it reaches a critical state. At first, the thin shell of hydrogen rests on the dwarf's crust, held there by crushing gravity. Nothing happens. The star is quiet. But the more material is added, the greater the pressure becomes. The bottom layer of this hydrogen envelope is compressed by the weight above it, and temperature begins to rise. Not gradually, but exponentially. This temperature and pressure increase continues unnoticed for years. Telescopes may detect subtle changes in the system's output, a flicker in brightness here, a change in spectral lines there, but overall, the system appears stable. Beneath the surface, though, the conditions are approaching the ignition point. The magic number is around 10 million Kelvin. At this point, hydrogen nuclei are squeezed together so tightly that fusion can begin. But here's the terrifying part: once fusion starts, it cannot be controlled. Normal stars like our Sun regulate their fusion via expansion and convection. If too much energy is released, the outer layers expand, reducing the pressure and cooling the core, a kind of built-in thermostat. But a white dwarf has no such mechanism. Its surface is inert and degenerate, meaning that its electrons are packed to their quantum mechanical limit. There is no expansion, no moderation. So when fusion begins, it runs away almost instantly. In seconds, a chain reaction unfolds. Fusion rips through the hydrogen layer like fire in a dry forest. Temperatures skyrocket to hundreds of millions of degrees. The accumulated gas is no longer held in place. It is blown outward in a titanic explosion that releases the energy of hundreds of trillions of hydrogen bombs. This is the nova event, the visible reawakening of the blaze star. The light reaches Earth a few days later. Astronomers around the world may see the system brighten from magnitude 10 to magnitude 2 or even brighter. For a brief moment, a star that was invisible to all but the most dedicated observers becomes a spectacle. To the untrained eye, it looks like a new star has appeared in the sky. But to those watching, it is the culmination of decades of anticipation. The white dwarf has once again reached its limit. Now, why 80 years? That number isn't exact. It's an average based on past eruptions and models of mass transfer in the TCRB system. The eruption of 1866 marked the first modern documentation. The next occurred in 1946, 80 years later. Predictions for the next one have centered around the 2020s, based on that historical precedent, combined with modern observational data suggesting that the mass transfer rate and the accretion disk behavior are again reaching critical conditions. But this interval is not guaranteed. It could be 77 years. It could be 84. Slight variations in the red giant's wind, magnetic fields, orbital eccentricity, or even subtle gravitational wobbles could alter the timing. The cycle also depends on whether the white dwarf retains any mass between eruptions. If each nova event causes the dwarf to lose exactly the same amount of mass it gained, the process could repeat indefinitely, a kind of perpetual stellar reset. But if even a tiny fraction of that hydrogen remains fused and locked into the star, its mass creeps upward. That would change the ignition conditions, possibly shortening the cycle. Or worse, accelerating it toward a final supernova. For now, we believe the TCRB white dwarf accumulates just enough mass in those 80 years to reach the pressure and temperature needed for surface fusion, triggering a nova but not a collapse. It is a balancing act so delicate that it defies belief. And yet, for at least 2 known cycles, it has succeeded. From a distance, this 80-year rhythm seems almost poetic, a cosmic heartbeat pulsing through generations of humanity. A child born during the last eruption would have lived a full life, perhaps had children, maybe even grandchildren, before the star stirred again. Astronomers from the 1940s are gone now, but their records remain. And the telescopes of today, more advanced, more precise, and scattered across the globe and space, are watching for the next pulse. But unlike a human heart, the nova cycle is not a guarantee of continued life. It is a countdown. A warning. A reminder that one day, this balance could fail. And when it does, the 80-year rhythm may give way to a singular, final blaze, a supernova so bright it could outshine the moon and be visible in daytime skies. Until then, we wait. And we watch. The cycle ticks onward. Quietly. Invisibly. Every hydrogen atom that crosses the void brings us one step closer. T Coronae Borealis is recharging, a time bomb resetting itself with gravity and fire. And soon, it may go off again. On a quiet night in May 1866, the sky over Europe looked much as it always had. The stars glimmered in their usual places, silent guardians of the heavens. But then something changed. Something so sudden and so spectacular that it stirred both seasoned astronomers and curious stargazers into a frenzy of observation and speculation. A new star had appeared in the constellation of Coronae Borealis, a star that had not been seen the night before. It was not a slow brightening, nor a subtle shift, it was a blazing light that erupted almost overnight. The year 1866 would become etched into astronomical history as the moment when T Coronae Borealis first introduced itself to humanity, or rather, reintroduced itself, though no one knew it then. The star flared to magnitude +2, making it one of the brightest stars in that part of the sky. For comparison, that's bright enough to rival Polaris, the North Star, and far more luminous than the faint stars that usually make up the Coronae Borealis constellation. It would have caught the eye even of casual skywatchers. But in the 19th century, it was the professional and amateur astronomers who would first document and attempt to explain the phenomenon. And what they saw deeply puzzled them. One of the first and most detailed observations came from the English astronomer John Birmingham. He was the one who formally reported the nova to the scientific community. It was a time when astrophysics was still in its infancy, and the idea of a star suddenly increasing in brightness, then fading again, seemed almost mythical. Some even questioned whether it was a new celestial body entirely. Was it a new planet? A comet? An atmospheric phenomenon? But as more observatories turned their telescopes to the new light, it became increasingly clear that this was something far more exotic. Astronomers of the era had recently begun to use spectroscopy to analyze starlight, a revolutionary technique at the time. William Huggins, another pioneer in the field, trained his spectroscope on the flare and noticed something strange. The light from the star revealed bright emission lines, particularly of hydrogen, instead of the usual absorption spectrum seen in most stars. This suggested that TCRB wasn't simply brightening due to proximity or reflection. It was emitting its own intense radiation from extremely hot gas. This was the first clue that a violent process was at play. It was Huggins who proposed the bold idea that this was not a new star, but a known star that had suddenly and violently flared in brightness. That idea was both exciting and unsettling. Until then, stars had been viewed as fixed, unchanging, eternal. But here was a star, one from an otherwise unremarkable part of the sky, that had erupted like a celestial volcano. The event sparked public fascination. Newspapers reported on the new star in Coronae Borealis, and for a brief time, the general public turned their gaze upward in wonder. But as weeks passed, the star began to fade. By early June, it had already dimmed significantly. And within a couple of months, it had vanished from naked eye view entirely. Astronomers documented its decline with great care, noting that its brightness dropped rapidly, much faster than any of the classical novae known at the time. It became clear that this was not the slow death of a star, but a sudden burst followed by an eerie return to silence. By the end of 1866, T Coronae Borealis had faded back into obscurity, a ghost of its former brilliance. For decades, it would remain a quiet, dim point in the sky, known only to those who remembered the great blaze and kept its coordinates marked. And during that silence, theories began to form. The idea of binary stars, systems of two stars orbiting each other, was gaining traction. Some speculated that TCRB might be such a system, and that the eruption was the result of matter transfer or collision. Others argued that it might be a totally unique object, a singular phenomenon never to be repeated. No one suspected that it would erupt again. At the time, the term, recurrent nova, didn't even exist. Novae themselves were only just beginning to be understood, and the 1866 eruption was among the earliest detailed records of such an event. It would take decades, and another eruption, before astronomers would realize that what they had witnessed in 1866 was just one beat in a much larger rhythm. Yet the significance of the event cannot be overstated. The 1866 nova of TCRB helped ignite an entirely new field of astrophysical inquiry. It demonstrated that the night sky is not immutable. Stars are not fixed and eternal. They are dynamic, evolving, sometimes erupting in sudden, brilliant violence. The eruption was also one of the first to be studied using spectroscopy, paving the way for modern stellar classification and the understanding of nuclear processes in stars. Most of all, it showed that stars could change, not gradually, over billions of years, but in a single night. And even though observers in 1866 had no idea that they were witnessing a cycle, their records, the sketches, the light curves, the magnitudes, the spectral lines, would become the foundation for future generations to piece together the true nature of TCRB. They did not know it yet, but the blaze star was not finished. It had only just begun. 80 years after its first recorded blaze lit up the sky in 1866, the world had changed dramatically. The horse-drawn carts of Victorian England had given way to automobiles and airplanes. The flicker of gas lamps had been replaced by electric lights. Telescopes had grown more powerful, photography had become widespread, and a world fresh out of World War II had entered a new scientific age, one that would include rockets, nuclear physics, and soon, space exploration. But amidst all this transformation, something ancient stirred again in the night sky, something that had been silent for decades. In February 1946, T Coronae Borealis exploded once more. This time, the world was ready. Unlike the 1866 eruption, the 1946 event was observed with the full force of 20th century astronomy. Radio telescopes were beginning to emerge, Photometric measurements were far more precise, and astronomers had decades of accumulated knowledge about binary systems, stellar evolution, and novae. When TCRB reawakened, it didn't catch the scientific community off guard, but it did thrill them. After all, this wasn't just a brightening, it was the confirmation of a mystery that had quietly endured for 80 years. That this was not a one-time event, but a recurrent nova. The term had been coined only a few decades earlier, and now TCRB stood as one of the most spectacular examples of such systems. The eruption began on February 9th, when astronomers noticed that the star had begun to brighten. By the next night, it had reached a magnitude of approximately 2.0, just like it had in 1866, suddenly visible to the naked eye, even in suburban skies. The rise was rapid, taking place over roughly 24 hours. It was dramatic and unmistakable. A star that had slept in silence for generations was suddenly among the brightest in its region of the sky. But unlike in 1866, this time telescopes across the globe were ready. Photographs were taken immediately. Spectroscopic measurements were gathered. Astronomers began documenting the light curve, the plot of brightness versus time, and tracking every nuance in its behavior. What they found confirmed what many had only suspected before. This nova was caused by a thermonuclear explosion on the surface of a white dwarf, triggered by the accretion of hydrogen from a red giant companion. The theoretical models of mass transfer, degenerate pressure, and runaway fusion were now matched by direct observations. The light curve from 1946 was steep, a near vertical climb to maximum brightness, followed by a rapid decline. Within 30 days, the star had faded back to magnitude 9. Within 2 months, it was all but invisible to the unaided eye again. But in those few weeks, it had revealed much about itself. Spectroscopic readings showed intense emission lines of hydrogen, helium, and other elements, classic signatures of an explosive ejection of material. The speed of the ejected shell was estimated to be around 1,500 km per second, consistent with the thermonuclear nova model. This event didn't just confirm TCRB's classification as a recurrent nova, it also pushed forward our understanding of these rare systems. Astronomers began to model the exact mechanisms involved, how long it took to build up the hydrogen envelope, how much mass needed to be accreted, and how the white dwarf's mass and temperature influenced the timing of the eruption. It became clear that the white dwarf in TCRB is unusually massive, likely nearing the Chandrasekhar limit, and that the accretion rate from the red giant is high enough to sustain repeated novae on human timescales. Beyond the scientific community, the 1946 eruption also made a mark on the public imagination. Newspapers picked up the story. Amateur astronomers pointed their backyard telescopes toward Coronae Borealis. Observatories invited schoolchildren and curious citizens to witness the fading light of a star that had gone rogue. For a few weeks, TCRB captured the attention of a war-weary world, a rare cosmic display that transcended. The eruption also gave rise to new questions. Would it erupt again? And if so, when? By comparing the 1866 and 1946 events, both in brightness and timing, astronomers began to estimate the recurrence interval, roughly 80 years, give or take a few. This was not exact, of course, but it gave scientists a benchmark. If the cycle held, the next eruption could be expected sometime around the 2020s, our current era. And with that realization, TCRB began a third life, not as a silent point in the sky, or as a curiosity of the past, but as a watchpoint for future study. From 1946 onward, observatories began tracking it periodically, cataloging its fluctuations in brightness, its spectral behavior, and any signs that it might be preparing to erupt again. It also became a testbed for theories about Type Ia supernovae. Could TCRB, after many more cycles, accumulate enough mass to trigger a final, destructive detonation? Could it cross the Chandrasekhar threshold and become one of the brightest supernovae visible from Earth? These questions weren't just hypothetical, they mattered for cosmology, for understanding how elements are forged in stellar explosions, and for using Type Ia supernovae as standard candles to measure the expansion of the universe. So while the 1946 eruption ended like the first, with a fade into darkness, its legacy was entirely different. It was not just another burst of light, but a scientific awakening. It showed that T Coronae Borealis is not a relic of the past but an active, evolving, and deeply important object in the modern astrophysical landscape. It helped shift the perception of novae from mysterious flare-ups to measurable, modellable processes, explosive, yes, but explainable. And most importantly, it started the countdown anew. If 1866 was a revelation, and 1946 was a confirmation, then the next eruption will be something else entirely. A convergence of technology, science, and human curiosity, all focused on a single star. We're not just wondering if TCRB will erupt again. We're watching it happen in slow motion. In the years following the 1946 eruption, T Coronae Borealis returned to its quiet slumber. But this time, it was under watchful eyes. Scientists had learned that this was no ordinary nova. It was a recurrent nova with a pattern. And patterns invite predictions. With the last eruption occurring in 1946 and the previous one in 1866, a rough 80-year cycle emerged, suggesting a potential third eruption sometime in the 2020s. That idea, once a speculative estimate, has now transformed into a full-scale scientific vigil. The star is not just being watched, it's being monitored obsessively. Modern astronomy has allowed scientists to peer into the mechanics of TCRB with unprecedented precision. Unlike the 19th or even the mid-20th century, today we have access to high-resolution spectroscopy, photometry, infrared monitoring, ultraviolet imaging, X-ray satellites, and radio observatories. All of these tools are now focused, at least periodically, on a single point in the Coronae Borealis constellation. Because unlike other recurrent novae that erupt more frequently, like Rs Ophiuchi or U Scorpii, TCRB takes its time. Its long cycle makes its eruption rarer and more significant. The build-up is slow, methodical, a cosmic suspense thriller playing out over decades. The idea that it could erupt again in the 2020s gained traction not only because of the 80-year average, but because of anomalous activity that began appearing around 2015. That year, astronomers noticed something odd. TCRB, which had remained relatively stable in brightness for decades, suddenly began to brighten. And not subtly. There was a statistically significant uptick in its visual and infrared light, a pre-eruption signature that hadn't been seen since just before the 1946 outburst. This behavior echoed what historical records suggested may have occurred prior to the 1866 and 1946 eruptions. A steady pre-blast brightening, sometimes accompanied by minor fluctuations, perhaps indicating increased accretion or changes in the disk structure. Astronomers called this period the pre-eruption plateau, and it's one of the most crucial pieces of evidence that TCRB is once again gearing up for an explosive show. Since then, the system has been placed under near-constant surveillance. Observatories like the American Association of Variable Star Observers, AVSO, along with professional teams using instruments like NASA's SWIFT and Hubble Space Telescopes, have begun cataloging every measurable change. Infrared telescopes are being used to detect heat from the dust and gas in the accretion disk. Ultraviolet instruments are watching for signs of increased fusion activity. And all the while, ground-based photometers continue recording fluctuations in brightness, sometimes down to fractions of a magnitude. Interest in TCRB has also ballooned because of its accessibility. When it erupts, it will be visible to the naked eye, a very rare trait for a nova in the modern era. Most stellar eruptions occur in distant galaxies or in obscure corners of the sky, but TCRB will erupt in a well-known constellation, near the bright Northern Crown. Amateur astronomers with backyard telescopes, or even just their eyes, will be able to witness the birth of a nova, possibly within their own lifetimes. This kind of event is as rare as a solar eclipse, but far less predictable. It won't just be a scientific moment, it will be a cultural one. Moreover, TCRB's next eruption won't just be a visual treat, it will be a multi-wavelength event. Instruments will be ready to catch it across the electromagnetic spectrum, from X-ray satellites to radio dishes, from wide-field optical surveys to time-domain monitoring systems like CTF, Zwicky Transit Facility. Astronomers hope to capture the entire event in real time, from the very first moment hydrogen ignites on the white dwarf's surface to the final fading embers of ejected material weeks later. Adding to the urgency is the fact that this might be our last chance to witness a nova from TCRB in its current form. There are speculations that the system is evolving. Some models suggest that the white dwarf is gaining mass with each eruption, possibly creeping closer to the Chandrasekhar limit. If this is true, then future eruptions might grow more powerful, more frequent, or culminate in something even more final, a Type I supernova. The 2020's eruption, if it comes, could offer clues about how far along that path the system really is. But predictions remain delicate. Astronomy is not clockwork. While the 80-year cycle gives us a statistical window, there's no guarantee that nature will abide by our math. The eruption could occur earlier, or be delayed by a few years. Variables like the red giant's mass loss rate, magnetic field variations, disk instabilities, or even minor changes in orbital dynamics could shift the timeline. Still, all signs point to a system that is building towards something. The brightness variations, the UV signatures, the disk activity, they all whisper the same message, soon. And with every passing month, the anticipation grows. Conferences are beginning to include panels about TCRB. Observation campaigns are being coordinated internationally. Even amateur astronomers are checking the star nightly, submitting brightness data to the AAVSO in hopes of being the first to notice a sudden jump in magnitude. The global astronomy community is, in essence, holding its breath. This is not a drill. This is a celestial event nearly a century in the making. And when the sky finally flashes, when the red giant's gift ignites on the white dwarf's surface once more, it will be more than an astronomical milestone. It will be the fulfillment of a multi-generational vigil. A light seen by grandparents that now returns to the eyes of their descendants. A cosmic clock ticking toward zero. T Coronae Borealis is preparing to blaze again. The eruption of T Coronae Borealis is not a gentle awakening. It's a violent outburst, a thermonuclear detonation on the surface of a dead star, triggered by an invisible process that takes decades to reach its limit, then explodes in just hours. To the human eye, it's a sudden flare, a star that appears out of nowhere. But beneath that simple transformation lies one of the most extraordinary astrophysical mechanisms in the universe, a carefully balanced buildup of matter, a silent stacking of hydrogen atoms layer by layer, until pressure and temperature cross a catastrophic threshold. And then, in an instant, the entire system erupts. For years, even decades, the red giant in the TCRB binary has been pouring material into its dense companion. The white dwarf, a stellar core left behind after the death of a sun-like star, is a strange thing, no longer powered by fusion, but still unimaginably hot and dense. Its mass is crammed into a space about the size of Earth, but it has the gravitational pull of the sun, enough to tear apart atoms and distort space itself. This gravity draws in hydrogen from the red giant, not in dramatic torrents but in a steady, quiet siphon. The matter first forms an accretion disk, a spiraling structure of gas and plasma that gradually funnels onto the surface of the white dwarf. As this hydrogen-rich material accumulates, it forms a thin shell on the white dwarf's surface. The conditions in this shell are extreme. Pressure builds relentlessly as more matter piles on. The lowest layers of hydrogen are squeezed tighter and tighter, until the atoms themselves can no longer hold back the crush. The temperature inside the shell begins to climb, at first slowly, then exponentially, as the shell thickens and the weight increases. There is no fusion yet. No light. No signal. Just pressure, density, and time. Then, finally, the critical moment arrives. At roughly 10 million Kelvin, the temperature in the lower hydrogen layer crosses a threshold where proton-proton chain fusion, the same reaction that powers our Sun, becomes possible. But on a white dwarf, things are very different from a main sequence star. There is no convection zone to distribute heat, no outer layers to expand and stabilize the fusion. The white dwarf's surface is a quantum-degenerate environment, meaning it resists expansion. The more pressure added, the more it pushes back, not with flexibility, but with rigidity. This is key. When fusion starts, the star can't relieve the pressure by expanding, so the temperature continues to rise unchecked. This leads to a runaway thermonuclear reaction. Once fusion begins, it ignites more fusion in the surrounding material, a chain reaction that spreads laterally across the entire shell of hydrogen in a matter of seconds or minutes. Imagine striking a match and setting fire to a thin layer of gasoline covering a sphere. The explosion would encompass the whole surface almost simultaneously. That's what happens here, a detonation across the white dwarf's entire surface, releasing energy equivalent to 10 ergs, about 1,000,000 times more powerful than the largest hydrogen bombs ever created on Earth. This explosion doesn't destroy the white dwarf, at least not yet. Instead, it blasts away the accumulated hydrogen shell in an enormous expanding wave of plasma and light. The expelled material races outward at thousands of kilometers per second. Shockwaves ripple through the accretion disk and the binary system. A flood of photons escapes, traveling across the cosmos until, a few days later, they reach Earth. To observers here, it's as if a new star has suddenly appeared. But it isn't new. It's a star that has been silently preparing to erupt for 80 years. This moment, the eruption phase, is stunning in both speed and scale. Within a single day, the brightness of TCRB skyrockets, going from a faint 10th magnitude to a blazing 2nd magnitude or brighter. That's a jump of thousands of times in luminosity. A star invisible to the naked eye suddenly becomes brighter than nearly all others in its constellation, an intruder in the familiar crown of Coronae Borealis. For a few precious days, it commands the sky, demanding attention from astronomers, photographers, and anyone else lucky enough to look up at the right time. The surrounding environment is flooded with high-energy radiation. X-rays, ultraviolet light, and shock-driven winds ripple outward. The ejected shell, mostly ionized hydrogen and helium, interacts with the white dwarf's magnetic field and the remaining accretion disk, generating turbulence, light echoes, and shock fronts. The entire binary system is temporarily transformed into a glowing cloud of radioactive gas, expanding outward while the white dwarf itself shrinks back into dormancy. Yet despite the violence, this eruption is not the end. The white dwarf survives, battered, perhaps slightly altered, but intact. The hydrogen shell is gone, but the red giant is still nearby, still overflowing its Roche lobe, still ready to resume the slow dance of mass transfer. The accretion disk reforms. Hydrogen begins piling up again. The nova cycle restarts. But the real mystery is whether all of the accreted hydrogen is blown off. If even a fraction of it is fused into helium and retained, the white dwarf gains mass, and that pushes it incrementally closer to the Chandrasekhar limit, the tipping point at which gravity overwhelms electron degeneracy pressure and triggers a core collapse. That's not what happens during this eruption. But one day, after perhaps dozens more cycles, it could. And that possibility lends a quiet, haunting tension to every blast of light. Each eruption is not just a dramatic reset. It's a possible step toward destruction. For now, though, what happens during a nova is not the death of a star, but its reignition, a momentary blaze in the cold dark, a fire fueled by the gift of another star. It is a relationship defined by gravity and destruction, by fusion and rebirth. And it's happening in real time, with the next eruption drawing closer every day. We may soon see it unfold again. And this time, we'll catch it in more detail than ever before, from its first flicker to its final fade, from the hydrogen buildup to the runaway blaze. And when it happens, we'll be witnessing a rare, violent heartbeat of a binary system trying to hold itself together, one more time. One of the most stunning and immediate aspects of T Coronae Borealis' eruptions, the very thing that draws amateurs and professionals alike to their telescopes with urgency, is just how dramatically and suddenly this quiet star transforms into a naked-eye spectacle. The change in brightness is not subtle. It's not gradual. It is violent, unmissable, and almost theatrical in its timing. A star that most people have never seen, that requires a decent telescope to detect on any ordinary night, suddenly becomes one of the brightest stars in its entire constellation, practically overnight. Under normal conditions, T Coronae Borealis has an apparent visual magnitude of about plus 10.0. To put that into perspective, the faintest stars visible to the naked eye under very dark skies are around plus 6.0 magnitude. So TCRB, in its dormant state, is completely invisible to unaided vision. It resides deep in the realm of telescope-only stars. Even then, seeing it clearly requires a moderately powerful scope or a long-exposure astrophotograph. For most of its life, TCRB is just a quiet flicker buried in the background sky, faint and ignorable. But then, in a matter of hours, it erupts. When the nova ignites, the white dwarf's surface detonating after decades of hydrogen buildup, the brightness climbs rapidly. And that rapid climb is not measured in months or even weeks. It can happen in a single night. Observers during the 1866 and 1946 eruptions recorded the star going from completely invisible to magnitude plus 2.0 or brighter in less than 24 hours. That is an increase in brightness of nearly 10,000 times. This kind of sudden surge is practically unheard of outside of nova and supernova events. Most stars that brighten do so over longer periods. Variable stars fluctuate, Cepheids pulse with predictable rhythms, and eclipsing binaries fade and reappear in slow cycles. But a recurrent nova like TCRB leaps. One night it's not there, and the next, it's demanding attention. Magnitude plus 2.0 puts TCRB in a very special category. That level of brightness means it's more luminous than Polaris, the North Star, which sits at around plus 2.0. It becomes brighter than any star in the Coronae Borealis constellation and one of the more prominent points in that entire region of the sky. Even in moderately light-polluted skies, an eruption of that scale would be visible. In a rural area with dark conditions, it would blaze out, unmistakable. And if the next eruption surpasses historical brightness records, as some models suggest it could, based on changes in mass accumulation rates and potential differences in the amount of hydrogen accreted, it might even climb to magnitude plus 1.0 or brighter. At that point, it would rival stars like Deneb or Altair. It wouldn't quite reach the brilliance of Sirius, but it would absolutely dominate the crown of Coronae Borealis and become a beacon for skywatchers around the world. What makes this so profound is how unpredictable the visibility window is. Because the eruption is so sudden, and because TCRB is only visible in certain seasons, there's an element of chance involved in catching the exact moment it flares. Will it erupt during a moonless night? Will the skies be clear? Will it happen when Coronae Borealis is high in the evening sky or hidden in daylight hours? These questions fuel both excitement and anxiety in the astronomical community. No one wants to miss it, especially since this is a once-in-a-lifetime event. Once TCRB reaches its peak brightness, it doesn't stay there long. Historical records show that the nova's decline is swift. From peak to invisibility takes a few weeks, and the sharpest drop happens within the first 10 days. By magnitude standards, it begins to dim rapidly after hitting maximum. Observers need to act quickly. If you wait too long, it's gone, not forever, but for another lifetime. This urgency adds a layer of emotional gravity to the event. We are not just observers, but witnesses to something fleeting, something cosmic that blinks into view and then vanishes again for another generation. To quantify the leap from plus 10.0 to plus 2.0 magnitude, every decrease by 1 in magnitude equals about 2.5 times more brightness. So going from 10 to 9 means the star is 2.5x brighter. From 10 to 8, it's 2.5 times 2.5 is equal to 6.25 times brighter. The math compounds fast. From plus 10 to plus 2 is a brightness increase of nearly 1600 times, and from plus 10 to plus 1 is over 4000 times brighter. If the next eruption pushes to magnitude 0 or even slightly into the negatives, which is theoretically possible if conditions are just right, we could be talking about a brightness increase of over 10,000 times. And unlike a supernova, which destroys the star in the process, TCRB doesn't die after its blaze. It dims, recovers, and begins the process again. It returns to that near-invisible plus 10.0 magnitude, where only a dedicated few continue to watch it. But for that 1 week, that brief burst of fire, it is among the brightest lights in the sky. We are standing at the edge of such a moment now. The star is stirring. The brightness is shifting. The systems tracking it are humming. At any time, any night, that leap from darkness to brilliance may come. And when it does, no one with eyes to the sky will miss it. T Coronae Borealis is not alone in its behavior, but it is rare. Among the stars that erupt as recurrent novae, only a handful are known to astronomers, and each of them tells a different version of the same stellar story. A white dwarf siphoning matter from a companion until it erupts in a thermonuclear firestorm. But in that chorus of cosmic explosions, TCRB holds a distinct note. Its rhythm is slower. Its eruptions are more separated in time. And the characters in its binary dance, particularly the red giant donor, set it apart from others in the same category. To appreciate just how unique TCRB is, it helps to compare it to two of the most well-known recurrent novae in our galaxy, RS Ophiuchi and U Scorpii. Let's begin with RS Ophiuchi, a recurrent nova that has erupted multiple times over the last century, most recently in 2021. Like TCRB, RS Oph is a binary system consisting of a white dwarf and a red giant, a similar configuration, but one that operates on a more frequent and energetic schedule. RS Oph erupts roughly every 15 to 20 years, making it one of the most active recurrent novae in our galaxy. These frequent outbursts are due to a high accretion rate. The red giant in RS Oph is continuously shedding matter at a rate that allows the white dwarf to accumulate enough hydrogen for ignition much more quickly than in TCRB. During its eruptions, RS Oph typically reaches about magnitude plus 5.0, making it visible to the naked eye in dark skies, though not as brilliantly as TCRB, which has reached magnitude plus 2.0 or brighter. This difference in brightness is partly due to distance, and partly due to the amount of material ejected and the conditions of the explosion. RS Opha's eruptions are fast and furious. They brighten quickly and fade just as rapidly, with strong emissions across X-ray and radio wavelengths. In fact, RS Oph has become a favorite for multi-wavelength studies because its frequent outbursts allow astronomers to plan observing campaigns well in advance. It's like a laboratory that reboots every 2 decades. By contrast, TCRB plays the long game. Its cycle, roughly 80 years, means each eruption is a generation-spanning event. There's a mystique to TCRB that RS Oph lacks, simply because we don't get to witness it often. When TCRB flares, it's not just a nova, it's a historic moment. And because of the longer interval, there's a possibility that more mass accumulates before each eruption, leading to potentially more energetic outbursts. It's not just about what happens, it's about the scale of anticipation. Then there's U Scorpii, a very different kind of recurrent nova altogether. U SCO is also a binary system with a white dwarf, but its donor star is not a red giant, but a subgiant or evolved main sequence star, and the two stars are packed tightly together, with an orbital period of just about 1.2 days. That proximity means the white dwarf in U SCO is fed at an extraordinarily high rate. As a result, U SCO erupts approximately every 10 years, one of the shortest known cycles for any nova system. The eruptions of U SCO are extremely fast. It can rise to magnitude plus 7.5 and then fall back below magnitude plus 14 within just a few days. This rapid eruption and decline make U SCO one of the fast novae, and a subject of intense interest for time-domain astronomy. These events are so fleeting that they challenge astronomers to react quickly. If you're not watching the right patch of sky at the right moment, you might miss it entirely. But while it fades fast, U SCO teaches us a great deal about mass transfer physics and the delicate balancing act of white dwarf stability. What sets TCRB apart from both RS Oph and U SCO is the interplay between time, scale, and visibility. It erupts less frequently than both. It shines more brightly at its peak. And its red giant companion makes it more similar in structure to RS Oph than U SCO, but with a quieter, more suspenseful buildup. TCRB's long dormancy and rare appearances give it a mythic status, an astronomical event that feels more like an eclipse of a generation than a recurring phenomenon. There's also the matter of what lies ahead. In all three systems, TCRB, RS Oph, and U SCO, the white dwarfs are likely gaining mass. They are not merely surviving eruptions, they are changing because of them. If the mass of the white dwarf in any of these systems crosses the Chandrasekhar limit, it will no longer erupt as a nova. Instead, it will collapse inward and trigger a Type I supernova, a far more violent, final, and bright explosion that would completely obliterate the white dwarf. Among these systems, TCRB is often viewed as a prime candidate for this future fate. Its white dwarf is believed to be very close to the Chandrasekhar limit, perhaps more so than USCO or RSOF. If that's true, the next few eruptions may be among its last. One day, there may be no dimming after the blaze, only an explosion that outshines its galaxy. Until that day, each of these novae continues its cycle, erupting, fading, accumulating, preparing. TCRB may be the slowest of the three, but when it flares, it commands more attention than any of them. It is the blaze star not just by nickname, but by nature, a celestial fire that waits, then flares like a lighthouse in the sky, guiding generations of stargazers to look up in awe. There are thousands upon thousands of stars that flicker in the night sky. Some burn steadily, others pulse with rhythmic intensity. A few flare up in dramatic outbursts. And among this tapestry of cosmic light, one star has captured human fascination across generations, not because it is the brightest, or the closest, or the most mysterious, but because of what it does only once in a lifetime: it erupts. And not just once, but again and again, in a silent rhythm that only reveals itself every 80 years or so. This is what makes T Coronae Borealis so famous. TCRB isn't a household name in the way that Polaris or Sirius might be. But within the world of astronomy, both amateur and professional, it is a celebrity of a different kind, the kind that commands reverence for its rare appearances. The kind of star that ignites anticipation not every week or year, but every generation. Its fame is rooted in visibility, repeatability, and a nickname that feels like something lifted straight from a science fiction epic, the Blaze Star. That nickname wasn't given casually. It's a title earned, not just once, but twice. First in 1866, when skywatchers observed a sudden new star lighting up the Coronae Borealis constellation, reaching a brilliance that rivaled the stars around it. That appearance was sudden and unexplained. Then again in 1946, when it did the impossible, it returned. The exact same star, quiet for 80 years, erupted once more. That act of recurrence shocked and delighted astronomers, who had no idea at the time that such behavior could even happen. It was this cycle, this awakening and slumber, that gave TCRB its legendary aura. Unlike one-off novae that flare and vanish forever, TCRB was doing something else. It was telling time. In the stillness of the sky, it pulsed like a slow cosmic metronome. It wasn't just a flare. It was a promise, a clock buried in the stars. And the reason it became famous wasn't only because of what it was, but also because of what it allowed us to do: prepare. Predicting a nova is a rare privilege in astronomy. Most cosmic explosions are sudden, violent surprises. A supernova in a distant galaxy might flash and fade before we can even point a telescope at it. But TCRB gave us warning. The intervals between its eruptions, though not exact, were close enough to allow entire generations of astronomers to say, "It's coming." This anticipation has made TCRB the center of an extraordinary global effort. Over the past few decades, telescopes around the world, from small backyard setups to multi-million-dollar observatories, have been watching it closely, monitoring its light curve, measuring its spectral emissions, listening for whispers of change. Few other stars receive this kind of attention over such a long stretch of time. But it's not just the science that makes it famous. It's the human connection. Because TCRB doesn't explode in obscurity. It erupts into view. During its outburst, it becomes a naked eye object, visible even from modestly light-polluted skies. Anyone, whether they own a telescope or not, can walk outside, look up toward the constellation Coronae Borealis, and see something astonishing. That accessibility has helped turn it into a phenomenon. It doesn't take a PhD to witness the event. Just a clear sky and a sense of wonder. And then there's the nickname, the Blaze Star. Unlike the dry alphanumeric designations most stars carry, the Blaze Star is something else. It's evocative, emotional, poetic. It doesn't just describe what happens, it frames it. It turns a celestial event into a story. That kind of name echoes in memory. It grabs headlines. It draws people in. When the media report on TCRB's next eruption, they won't say, "The variable star T Coronae Borealis has brightened." They'll say, "The blaze star is about to erupt again." That kind of linguistic power matters. Astronomy, after all, is a deeply human endeavor. We study the sky not only with instruments, but with imagination. The blaze star isn't just famous because it erupts. It's famous because it returns. It keeps a secret for decades, then reveals it in a flash. It's a celestial fire that reappears once per human lifetime, and that rhythm, that sense of recurrence, makes it feel alive. When people think of events in the sky they can actually witness, their minds turn to solar eclipses, meteor showers, comets. Rare things, but repeatable. Now, in the 2020s, a nova has joined that list, not just in textbooks, but in real time. And among novae, TCRB is special. It's not just a one-night wonder. It's a legacy star. It connects the astronomers of 1866 to those of today, and the observers of today to those of the 2100s. Every eruption is a page in an ongoing story, one whose next chapter may unfold at any moment. That's what makes it so famous. That's what makes it unforgettable. It blazes. And then it waits. And we wait with it. Beneath the awe and excitement that surrounds each eruption of T Coronae Borealis lies a deeper, more unsettling question, one that lingers behind the brilliant flash and fading embers. What if one day, this recurring nova doesn't just blaze and dim again? What if, instead of going dormant for another 80 years, it reaches the end of its cycle and explodes for good? This is not just a poetic notion or a speculative fantasy. It's a very real possibility grounded in hard astrophysical theory. The white dwarf at the heart of TCRB is walking a razor-thin line between temporary ignition and total annihilation. Every time it accumulates material from its red giant companion, it inches closer to a threshold that, once crossed, cannot be undone, the Chandrasekhar limit. This limit, named after astrophysicist Subrahmanyan Chandrasekhar, defines the maximum mass a white dwarf can sustain before its own gravity collapses it into oblivion. That critical value is approximately 1.4 times the mass of our Sun. Beyond this limit, electron degeneracy pressure, the quantum mechanical force that supports a white dwarf against gravitational collapse, can no longer hold back the immense inward pull. The result is catastrophic. The white dwarf undergoes a sudden thermonuclear disruption, not just on its surface, but throughout its entire core, releasing a staggering amount of energy in a matter of seconds. This is the hallmark of a Type I supernova, an event so powerful that it can briefly outshine an entire galaxy. Could this fate await TCRB? There are clues that suggest it might. The white dwarf in this system is already suspected to be quite massive, perhaps hovering near the Chandrasekhar limit already, possibly around 1.2 to 1.3 solar masses, according to various models. This is not unusual for recurrent novae. In fact, it's precisely why they are recurrent. A more massive white dwarf has a stronger gravitational pull, allowing it to gather material more quickly and reach the conditions for runaway hydrogen fusion with less accumulated mass. This is one of the reasons TCRB erupts at such long intervals. Its companion feeds it just slowly enough that the buildup takes decades rather than years. But each time that buildup ends in an eruption, not all of the mass is expelled. In theory, the explosive nova blast ejects most of the accreted hydrogen shell. However, simulations suggest that some fraction of the fused material is retained, especially helium and heavier elements formed during the brief fusion event. This retention, if it occurs, adds to the white dwarf's total mass, ever so slightly, after each cycle. Now consider the timescale. TCRB has likely been engaged in this cosmic dance for thousands, possibly millions of years. With each passing nova, it could be gaining just a little more mass, getting closer to the supernova tipping point. The current estimates of its mass suggest it may only need a few more nova cycles before it exceeds the Chandrasekhar threshold. And then? Then the eruption will not be one of surface fusion. It will be total, core-wide, irreversible destruction. The white dwarf will collapse inward until carbon and oxygen in its core ignite in a runaway chain reaction. The energy released will tear the star apart in a supernova visible across the entire galaxy. This wouldn't be just another temporary brightening. It would be the end of the system as we know it. There would be no remnant star, just an expanding shell of radioactive debris hurtling into space at thousands of kilometers per second. In place of a quiet binary pair, there would be a glowing cloud of gas, brighter than 1 billion suns, slowly fading over weeks and months. For astronomers, the possibility of a nearby Type I supernova is both terrifying and thrilling. These events are used as cosmic yardsticks, standard candles that help measure the expansion of the universe. They are critical tools in the discovery of dark energy. And yet, we have never witnessed one from so close. Most Type I supernovae are seen in distant galaxies, far beyond the Milky Way. If TCRB went supernova, it would be the first galactic Type I explosion observable in modern scientific history. But it also raises concerns. TCRB is about 3,000 light-years away, far enough that its supernova wouldn't pose any immediate threat to life on Earth, but close enough that it would dominate the sky. During the peak of the explosion, it could rival the full moon in brightness, casting shadows at night, visible even during the day. For weeks or even months, it would be impossible to ignore, a cosmic fire burning in the place where once a small, faint star quietly pulsed. It's worth noting that this outcome is not guaranteed. Some models suggest that recurrent novae can remain stable for hundreds of thousands of years without ever reaching the Chandrasekhar limit. Others propose that mass loss from eruptions might cancel out any gain. There are also debates about whether accretion from a red giant is efficient enough to push a white dwarf all the way to collapse, or if angular momentum and magnetic fields can stall the process. But the threat is real. TCRB is being watched closely not just because of its spectacular eruptions, but because it may be on the edge of stellar suicide. Each nova it experiences might be one step closer to the final flash. And if that flash comes, it will be unlike anything we've ever seen. A star that was once quiet, then blazing, then quiet again, will go silent forever, leaving behind not a dimming trail, but a newborn supernova remnant, expanding into space. In this way, TCRB becomes not just a variable star or a nova, but a time bomb, ticking quietly in the night sky. When it explodes, it will write its final chapter in light. And the universe will remember it. T Coronae Borealis isn't just a rare spectacle, it's a working model of stellar evolution in action. A natural laboratory, suspended thousands of light-years above Earth, where astronomers can study some of the most complex and violent processes in the cosmos. For all its beauty and drama, what makes TCRB truly invaluable to science is how it ties together some of the biggest questions in astrophysics. How stars interact, how mass is exchanged between them, how eruptions are triggered, and what happens when stellar remnants inch toward catastrophic ends. At its core, TCRB offers an intricate case study in binary evolution. Most stars in the universe don't live alone. They exist in pairs or clusters. But not all binaries are as intimately bound as the ones that create recurrent novae. In the case of TCRB, we're looking at a close binary system involving a white dwarf, a remnant of a star that once burned like our Sun, and a red giant, a swollen, dying star whose outer layers are loose enough to spill across the void between them. This isn't just a gravitational partnership. It's a process of mass transfer, one star physically feeding the other. Understanding how this mass transfer works is essential to unraveling countless other phenomena in the universe. In TCRB, the red giant is overflowing its Roche lobe, a gravitational boundary around each star in a binary system that defines the region where material is gravitationally bound to one star or the other. Once a star expands beyond that limit, its outer material begins to drift toward the companion, creating a steady stream of gas that spirals into the white dwarf, forming a rotating accretion disk. This disk isn't just a passive conveyor belt. It's a zone of extreme temperatures, magnetic instabilities, and friction. As the material swirls inward, it heats up, emitting radiation in various wavelengths, particularly in the ultraviolet and X-ray bands. By observing these emissions, scientists can infer the rate of accretion, the composition of the gas, and the magnetic environment around the white dwarf. These are critical parameters for determining how long it will take for the nova to erupt again, and whether the white dwarf is gaining mass or losing it. Moreover, TCRB allows scientists to test nova mechanics, the chain of events that lead from hydrogen accumulation to runaway fusion. While thermonuclear physics can be simulated in labs and computers, there's no substitute for a real-time, observable eruption. Every time TCRB flares, astronomers can capture data across the electromagnetic spectrum, analyzing how the explosion unfolds, how energy is released, and how material is ejected. The light curves, spectral lines, and shock signatures gathered during an eruption help refine models of hydrogen ignition, fusion propagation, and envelope detachment. And because TCRB is a recurrent nova, one of only a dozen or so known in the Milky Way, it provides a chance to study how nova systems evolve over time. A one-off nova might be impressive, but it doesn't tell us much about long-term trends. TCRB, on the other hand, offers a baseline and a comparison point. We have data from its eruption in 1866, and more detailed data from 1946. With the next eruption imminent, we're about to add a third high-resolution dataset to the sequence, a generational leap in observational fidelity thanks to modern instruments. By comparing eruptions across centuries, we can study how the system's mass, composition, and behavior have changed. TCRB also serves as a bridge between stellar and galactic phenomena. Recurrent novae like this are thought to be one of the progenitor channels for Type Ia supernovae, which are some of the most important tools in cosmology. These supernovae act as standard candles, objects of known intrinsic brightness that allow astronomers to calculate cosmic distances. It was through studies of Type Ia supernovae that scientists discovered the accelerating expansion of the universe and inferred the existence of dark energy. But despite their importance, the exact stellar mechanisms that produce Type Ia events are still under debate. Systems like TCRB provide real, observable candidates for the single degenerate path, where a white dwarf accretes mass from a non-degenerate companion until it crosses the Chandrasekhar limit and explodes. Beyond the supernova question, TCRB is helping astrophysicists refine our understanding of stellar life cycles, especially in binaries. The end states of stars aren't always clean transitions from main sequence to white dwarf, or from giant to supernova. In many cases, as TCRB shows us, dying stars interact, exchanging mass, triggering explosive episodes, and altering each other's evolution. This complexity is critical for interpreting observations of distant galaxies, where integrated light from billions of stars must be decoded through models built on examples like TCRB. Another scientific bonus of studying this star is its accessibility. TCRB is close enough and bright enough that both professional and amateur astronomers can contribute to its monitoring. This creates a rich dataset spanning decades, with light curves recorded from backyard observatories all the way up to Hubble-class instruments. It's a rare example of citizen science converging with elite astrophysics, giving the star a dual life as both a cultural and scientific phenomenon. And let's not forget the educational impact. Because TCRB erupts on human timescales and can be seen without advanced equipment during its peak, it serves as a teaching moment for astronomy students, science communicators, and the public. It connects everyday observers to processes that usually seem abstract or unreachable. When people hear that a star is about to explode, and that they can witness it themselves, they become emotionally and intellectually engaged. And that kind of engagement drives curiosity, funding, and the next generation of scientific discovery. TCRB matters because it is a cosmic intersection, where the personal meets the universal, where observation meets theory, and where time itself becomes a part of the experiment. We're not just studying a star. We're watching evolution in real time, learning from each flare, and piecing together the long and complicated story of how stars live, die, and affect the universe around them. This is science, unfolding in the night sky, and TCRB is one of its most luminous pages. When we look at T Coronae Borealis, we're not just observing a rare explosion or an astronomical curiosity. We are witnessing a system caught in the act of dying. But unlike the sudden drama of a supernova or the gradual fade of a solitary star, TCRB exists in a unique middle state. It is not dead yet. It is not entirely alive either. It is in transition, teetering on the edge of stellar oblivion, a rare phase that allows scientists to explore the winding, violent, and tangled pathways of stellar death in binary systems. And because we can watch it evolve, flare, and settle over time, TCRB has become a living laboratory, a dynamic and evolving system where nature reveals the fine print of how stars end. Most of us imagine stellar death as something straightforward. A star exhausts its fuel, collapses, explodes, or cools into a faint cinder. But in reality, especially in binary systems like TCRB, stellar death is not a clean or solitary act. It's a complex and prolonged interaction, shaped not just by a star's own mass and fusion processes, but also by what its companion does and takes. And TCRB embodies this complexity more vividly than almost any other known system. Here, we see two stars in very different stages of life: the red giant, swollen and dying, and the white dwarf, already dead, the ultra-dense, Earth-sized remnant of a once solar mass star. On their own, each star would follow a predictable path. The red giant would lose its envelope, eventually exposing a core that cools into a white dwarf. The white dwarf, without fuel, would simply radiate heat and grow colder and fainter over billions of years. But together, these two stars warp each other's destinies. The red giant's bloated outer layers are no longer bound tightly by gravity. Its outer atmosphere spills past the Roche lobe and is drawn into the white dwarf's grip. This is not a peaceful process. The white dwarf pulls in that matter, compressing and heating it in its intense gravity well. A slow, invisible transfer of death begins, where one star is giving up its substance to another that's already passed through the veil of nuclear fusion's end. This process doesn't just delay the inevitable, it rewrites it. Each nova event in TCRB is essentially a mini supernova rehearsal, a thermonuclear warning shot that the white dwarf still has fuel to burn, still has explosions to unleash. But these novae are not part of the white dwarf's original death. They are a resurrection by cannibalism, a secondary death cycle fueled by its companion's decay. The white dwarf is already inert at its core. It no longer fuses atoms. But by accepting stolen hydrogen from its red giant partner, it creates thin, temporary envelopes on its surface that can ignite under pressure. The result is a nova, a runaway nuclear flash that blows away the outer layer but leaves the white dwarf intact, for now. In this sense, TCRB represents a feedback loop of dying stars. The red giant is shedding mass that it will never regain. The white dwarf is taking that mass and using it to power brief rebirths of violence. And all the while, the mass balance is shifting. The red giant gets lighter. The white dwarf, possibly, gets heavier. This slow exchange is not just symbolic of death. It is death being drawn out, death being negotiated between two stellar corpses in waiting. Such systems are rare and precious to science precisely because this transition phase is so brief in cosmic terms. We're catching a binary pair in the last million years, maybe even the last 100,000 years, of its shared evolution. One blink of time in galactic history. Eventually, the red giant will lose too much mass to sustain fusion. It will contract and cool, becoming a white dwarf itself. At that point, the system may become a double-degenerate binary, two dead stars orbiting in silence. Or if the white dwarf gains too much mass too quickly, it may collapse into a Type I supernova before that can happen. Either way, the end is certain. But for now, we're watching the between time, a moment when death is not final but staged in eruptions, slow and theatrical. This transition phase also allows astronomers to observe envelope stripping, angular momentum loss, and accretion dynamics, all processes that are incredibly hard to simulate in lab settings or even in computer models without real-world data. By tracking the periodic novae of TCRB and the behavior of its companion star, researchers can test and refine equations about binary orbital decay, gravitational drag, and even the mechanics of disk turbulence, physical forces that determine the fate of millions of binary stars across the universe. And there's more. The material expelled during each nova eruption doesn't just vanish. It forms ejected shells of gas that can be tracked, mapped, and analyzed. These shells become fossil records of past eruptions, allowing astronomers to reconstruct the history of the system's explosions and compare it to what models predict. In the case of TCRB, observations of the space around it suggest that multiple eruptions have left scars, ghostly gas remnants that float just beyond the star system, invisible to the naked eye but detectable with the right filters and instruments. These expelled remnants aren't just academically interesting, they also represent the final return of stardust to the galaxy. Material forged and processed in the life and death throes of these stars eventually becomes part of the interstellar medium, the gas and dust that will seed future generations of stars. In this way, the death transition we're watching in TCRB is not an isolated act. It's part of the galactic ecosystem. One death feeds another birth. And if that wasn't profound enough, consider this. The energy from a nova eruption like TCRB's affects not only the immediate surroundings, but the chemistry of nearby interstellar space. It contributes to the enrichment of heavy elements. It sends shockwaves through surrounding gas clouds. Over millions of years, these echoes help shape the galaxy's structure and composition. So when we call TCRB a living lab for stellar death, we're not just using metaphor. It is genuinely alive with physics. It is pulsing with data. It is showing us, moment by moment, year by year, how stars die in pairs, how they steal from one another, how they flare and fade and feed the cycle of cosmic recycling. It is not a tomb. It is not a nursery. It is both. And we are lucky enough to be alive at the moment when it's flaring once more. Today, as T Coronae Borealis continues to inch ever closer toward its anticipated eruption, the eyes of the Earth are fixed upon it, not human eyes alone, but mechanical ones, scattered across mountaintops, deserts, and remote observatory stations around the world. These telescopes, both humble and grand, are tracking the blazed star with relentless precision. For astronomers, this is no longer a distant curiosity. It's a live experiment, and the countdown has already begun. Across the globe, ground-based observatories, some with wide-field cameras, others with finely tuned spectrographs, are dedicating more and more of their nightly observation time to a single point in the northern sky, the constellation of Coronae Borealis, where TCRB lies nestled, waiting. This star, dormant for nearly 8 decades, is now under intense surveillance. Its light, though faint to the unaided eye, is being dissected nightly, pixel by pixel, photon by photon, by instruments capable of detecting even the smallest fluctuations. Some of the most active participants in this vigil are professional observatories situated at high altitudes, where the atmosphere is thin and dry. The Roque de los Muchachos Observatory in the Canary Islands, the Mauna Kea Observatories in Hawaii, the European Southern Observatories La Silla and Paranal sites in Chile, all are capable of tracking faint stellar variations with extreme sensitivity. These observatories are uniquely positioned to gather both photometric and spectroscopic data, capturing how the star's brightness, color, and chemical signatures are changing over time. These aren't one-off observations. TCRB is now on nightly watch lists, included in long-term monitoring programs designed specifically to capture precursors to nova eruptions. Changes in the star's temperature, dips or spikes in brightness, even alterations in the infrared spectrum, all of these are being noted and analyzed in real time. Telescopes equipped with adaptive optics are resolving the immediate environment around TCRB, checking for asymmetries in the accretion disk, and searching for signs of dense gas clouds or jets forming near the white dwarf. In addition to the big institutional players, robotic telescope networks have become a key part of this 24/7 surveillance. Networks like the Las Cumbres Observatory Global Telescope Network, COGT, which operates fully automated telescopes in multiple countries, are observing TCRB on a near-daily basis. These robotic observatories can respond quickly to sudden changes in the star's brightness and offer an uninterrupted chain of observations thanks to their global spread. When one telescope goes offline for daylight, another on the other side of the Earth picks up the watch. Equally important is the contribution from amateur astronomers. And here lies one of the most compelling aspects of TCRB's story. Because the star is relatively bright compared to other novae, reaching as high as magnitude 2 or 3 during eruption, it falls well within the capabilities of backyard telescopes and even DSLR cameras. Enthusiasts from the American Association of Variable Star Observers, AVSO, and similar organizations worldwide have been tracking TCRB for years, many of them submitting daily visual estimates and photometric data. This community of amateur astronomers forms the grassroots backbone of TCRB's observational history. Some have been watching the star for decades, recording changes long before major observatories took serious notice. Their vigilance, often using simple telescopes and filters, helps build a continuous, high-resolution light curve that spans years. These amateur observers are often the first to spot early warning signs, a subtle shift in brightness, a slight dip in color, or a persistent anomaly that hints at deepening instability in the system. And the coordination is only growing more sophisticated. Shared online databases, automated alert systems, and real-time graphing tools allow observers across the planet to immediately upload and analyze each other's results. If TCRB were to brighten even slightly overnight, the global network would know by dawn. Astronomers from Spain, Chile, the US, Japan, and Australia would all be comparing notes by the next rotation of Earth. Some observers are even turning to spectropolarimetry, a method that can reveal the alignment and composition of gas around the star by analyzing how its light is polarized. These subtle cues can indicate whether the system is building up to another thermonuclear runaway, or merely fluctuating in a stable loop. Every data point helps refine the models, not just for TCRB, but for our broader understanding of recurrent novae as a whole. The coverage is so extensive that there are now dedicated observing campaigns focused entirely on TCRB. Several universities and research institutions have allocated telescope time months in advance, essentially reserving slots for the moment the eruption begins. The goal is to catch it in the act, not just the aftermath. Because no two nova events are ever identical, capturing the moment of ignition could provide invaluable insight into how mass accretion transitions into explosive fusion. A delay of even a few hours could mean missing that critical early flash, the burst of high-energy photons that announces the nova's arrival. Even solar observatories and radio telescope arrays are standing by. Should the eruption trigger significant outflows or shocks in surrounding space, low-frequency radio waves and soft X-rays may begin to pour out of the system, and terrestrial observatories, like the Very Large Array, VLA, in New Mexico, or the Atacama Large Millimeter/Submillimeter Array, ALMA, in Chile, will be able to trace those waves back to the eruption's core. This is all part of an unprecedented, planet-wide scientific anticipation. Few celestial objects receive this much attention outside of imminent asteroid approaches or rare transits of Mercury and Venus. But TCRB is different. It is alive, evolving, on the verge of transformation. And Earth is watching. For now, the star remains quiet, but only just. Observers have noted unusual dips and rises in brightness since 2015, and the system has shown more variability in the past 5 years than it has in decades. It is shaking, shimmering, whispering that something is coming. And thanks to this growing network of ground-based eyes, when that moment arrives, humanity will not be taken by surprise. We will see it. We will record it. And we will learn from it. As Earth-based observatories maintain their nightly vigil on T Coronae Borealis, a second, more powerful fleet waits in silence above us, space-based telescopes orbiting beyond our atmosphere, free from clouds, distortion, and even daylight. These instruments offer more than just a clearer view. They provide access to wavelengths that Earth cannot see, ultraviolet, X-ray, and the far infrared, critical frequencies where a nova like TCRB tells its deepest secrets. And when the blaze star erupts again, it won't just light up the night sky, it will trigger a coordinated response from the cosmos's most advanced machines. At the forefront of this celestial surveillance is NASA's Swift Observatory, a satellite built for one mission: to catch things in the act of exploding. Originally designed to detect gamma-ray bursts, Swift has proven itself invaluable for fast-response transient events like novae. It has already observed several previous nova outbursts, but TCRB is something special, a target known in advance, a slow-burning fuse rather than a random firecracker. Astronomers have Swift on standby, ready to observe the star at the first sign of eruption. Its instruments, particularly its X-ray telescope, XRT, and ultraviolet/optical telescope, UVOT, are uniquely suited to capture the earliest stages of thermonuclear breakout. Why is that important? Because during the initial moments of a nova, long before visible light reaches its peak, the eruption begins with a wave of high-energy photons. These X-rays and ultraviolet rays are signs of hydrogen fusion lighting off on the white dwarf's surface, like watching the very first sparks of a fire before it grows into a blaze. Earth's atmosphere blocks nearly all of this radiation, but space telescopes like Swift can see it directly. And by capturing this early light, astronomers can reconstruct exactly how fast, how hot, and how violent the explosion really is. But Swift is only the beginning. The Hubble Space Telescope, one of the most iconic instruments in astronomical history, is also part of the hunt. Though Hubble is aging, its suite of cameras, especially the Cosmic Origin Spectrograph, COS, and the Space Telescope Imaging Spectrograph, STEAS, can perform high-resolution spectroscopy in the ultraviolet. This is a goldmine for studying nova ejecta. Once TCRB erupts, Hubble can analyze the expanding shell of gas, identifying individual elements and ions, hydrogen, helium, carbon, oxygen, nitrogen, and even rarer metals forged or expelled during the fusion event. These spectra are fingerprints. They tell scientists how fast the gas is moving, what temperatures are involved, and how much mass was lost. Comparing the data from the coming eruption to that of the 1946 event will allow researchers to determine whether the system has changed, whether the white dwarf has grown closer to the Chandrasekhar limit, or whether the eruptions are becoming more or less violent over time. And because Hubble can resolve extremely fine detail, it might even capture structure within the ejected shell, rings, clumps, asymmetries, that speak to the underlying physics of the explosion. Perhaps most exciting of all, though, is the possibility that the James Webb Space Telescope, the most powerful space observatory ever built, may join the effort. Webb was not designed for transient events, but its infrared sensitivity makes it an ideal tool for tracking novae after the initial outburst, when dust begins to form in the cooling gas. TCRB, like many novae, is expected to produce dust and molecules in its wake, and JWST's instruments, particularly NIRSpec and MIRI, can see those features like never before. For the first time in human history, we may be able to watch dust form in real time in the aftermath of a recurrent nova. We'll be able to measure the temperature, composition, and growth of particles that will eventually drift into interstellar space, contributing to the next generation of stars and planets. Even before the eruption, JWST may play a role. In recent years, it has been used to observe accreting white dwarfs, and it's possible that as TCRB nears its outburst, Webb could observe the infrared brightening that often precedes ignition, an early warning sign that Earth-based telescopes have already picked up hints of. These signals, though subtle, may be more easily detected in space, where background noise is minimal and long exposures are possible without atmospheric interference. The ability of these space telescopes to observe in tandem with ground-based observatories creates a kind of multi-layered observatory network. When TCRB erupts, the event will be captured in visible light, ultraviolet, X-rays, and infrared simultaneously. This multi-wavelength approach is essential, because novae are complex. Their radiation output changes dramatically over time and across frequencies. What's bright in X-rays at first will fade and shift into infrared days later. Only by stitching together data from every available telescope can scientists build a complete picture. And all of this is coordinated. NASA, ESA, and observatories around the world have already begun issuing Target of Opportunity 2 proposals, which allows space telescopes to rapidly pivot their gaze toward a transient object as soon as it erupts. TCRB is considered one of the highest priority targets in this category. Scientists are essentially reserving telescope time now for an event that may happen tomorrow, or next month, or next year, because when it does, the clock will be ticking. This approach, combining the brute light-gathering power of Earth's largest observatories with the precision and wavelength range of space-based instruments, represents the cutting edge of transient astronomy. It's a field built not on slow surveys or static catalogs, but on anticipation, on waiting, on the promise that one day, without warning, the sky will change. TCRB is a keystone of this new observational model. And when it explodes, it will trigger one of the most coordinated, multi-instrument observing campaigns in the history of astronomy. We will not just watch the blaze. We will dissect it, in wavelengths visible and invisible, from telescopes on Earth and in orbit, across every continent and hemisphere. It will be a moment not just of light, but of understanding. The cosmos rarely shouts its intentions. More often, it whispers, subtle hints, faint flickers, patterns that only the most patient and vigilant observers can decipher. With T Coronae Borealis, those whispers have been growing louder since 2015. What once appeared to be just another dormant phase in its long and quiet orbit has begun to shift, almost imperceptibly at first, but now undeniably. Something is changing. And to those who understand how a star prepares to explode, the signs are as thrilling as they are ominous. For a recurrent nova like TCRB, the path to eruption isn't sudden. It's a long and delicate process, where matter is slowly stolen, temperature gradients shift, and the pressure on the white dwarf's surface builds toward a catastrophic threshold. And unlike a one-time nova or supernova where we are caught off guard, TCRB offers us a rare chance to see the run-up to a thermonuclear event. A cosmic slow burn that gives away its secrets one anomaly at a time. It began in earnest in 2015, when observers first noticed something strange. TCRB had entered a low-brightness state, a phenomenon not seen since the years leading up to its last eruption in 1946. At first glance, this might seem counterintuitive. Why would a star preparing to explode dim? But in the complex physics of accreting white dwarfs, this is exactly what one might expect. The dimming is likely linked to changes in the accretion disk, which temporarily becomes less luminous as mass flow rearranges or drops before reaccelerating again. This dimming wasn't just a footnote in the star's history. It was a repeat of a nearly identical pattern seen prior to the 1946 event. Historical records showed that in the years before that eruption, TCRB also underwent an anomalous fade, likely signaling a reconfiguration of mass transfer dynamics. The eerie similarity between these two fading events, 80 years apart, ignited excitement and urgency in the astronomical community. Could we be witnessing the same prelude to another explosion? Then came the brightening in the infrared. Over the past several years, observatories sensitive to longer wavelengths began reporting a gradual rise in infrared emission from the TCRB system. Infrared light, unlike visible or ultraviolet, can pierce through surrounding gas and dust, and it is often the first signature of heated material in the outer regions of a star or disk. In the case of TCRB, this infrared enhancement strongly suggests that material is piling up in the accretion zone. More mass. More heat. More instability. This is critical, because one of the major triggers for a nova is the mass threshold of accreted hydrogen on the white dwarf's surface. As the red giant continues to pour gas into the white dwarf's gravitational well, a dense shell of hydrogen accumulates. For months or years before the ignition, this shell begins to compress, heating up as gravitational energy converts into thermal pressure. If infrared light is increasing, it likely means that this shell is growing, perhaps faster than in previous cycles. And if it reaches a critical depth, it will ignite in a flash of runaway fusion. Astronomers have also observed changes in spectral lines, indicators of the chemistry and motion of gas in and around the system. The emission features in hydrogen alpha, a specific red wavelength of light tied to ionized hydrogen, have shown variability and broadening, a possible sign that the system is becoming more turbulent. In particular, this could reflect increased outflows or mass winds from the red giant, which in turn would feed the white dwarf faster, escalating the timeline toward eruption. Another intriguing sign involves the flickering behavior of TCRB's light curve. High-speed photometry has revealed short-term brightness fluctuations, lasting minutes to hours, that may be related to instabilities in the accretion disk. These flickers are more than just random noise. They are a pulse, a heartbeat of a system under pressure. They could be caused by clumps of matter spiraling inward, releasing bursts of energy as they crash closer to the white dwarf's surface. But perhaps the most convincing evidence lies in the pattern of historical repetition. When astronomers overlay the current behavior of TCRB with its profile from the years preceding the 1946 nova, the similarities are astonishing. Not just in the light curve and infrared activity, but in color indices, brightness dips, and even the timing of specific photometric features. It's as if the star is retracing its steps, walking down the same path that ended in a brilliant, system-altering eruption nearly a century ago. This repetition has led to a surge in predictive modeling, as scientists use both historical data and modern physics to estimate when the system will erupt again. Some models suggest that the nova may occur any time between now and the end of the decade, with a high probability around 2024 to 2026, a timeline that has led to intense global monitoring campaigns, including alert systems designed to notify astronomers within hours if a brightness spike is detected. It's worth noting that nova triggers are nonlinear. That is, the system can appear quiet right up until the moment of ignition. Unlike a volcano that might tremble or crack before an eruption, TCRB may not offer a dramatic precursor. It could simply flare to life in a single night, its brightness leaping from near invisibility to second magnitude in less than 24 hours. This is why the growing unease among astronomers is not based on panic, but on pattern recognition. The system is behaving too much like it did the last time for this to be ignored. In fact, some observers believe the window is narrowing fast. Recent increases in ultraviolet variability, as well as enhanced X-ray emissions from nearby regions of the sky, possibly linked to small outbursts or pre-nova heating events, suggest that the white dwarf's surface is already approaching critical pressure and temperature thresholds. If this interpretation holds true, we may be within months or even weeks of witnessing a cosmic event that no living person has seen since the post-war era. And unlike in 1946, this time, we're ready. We're watching from mountaintops and space stations, with robotic telescopes and billion-dollar satellites. We're listening in X-rays and feeling its warmth in the infrared. We are, in a very real sense, holding our collective breath, watching a silent star in a quiet constellation begin to stir, a star that has not screamed in nearly 80 years. But now, perhaps, it is clearing its throat. If T Coronae Borealis erupts in our time, and signs suggest it soon might, the experience will be unlike anything in modern astronomy. Not because it's the brightest nova ever seen, nor the most violent, nor the rarest. But because for the first time in human history, a recurrent nova of this magnitude will explode under full observational coverage, with Earth's most powerful instruments focused on it across every wavelength, from every angle, and in every corner of the globe and beyond. This will not be a silent explosion in the night sky. It will be a symphony of data, a cosmic event turned inside out in real time. So what will we see? It begins quietly, invisibly even. At first, deep in the compact inferno of the white dwarf's surface, hydrogen that has been slowly accumulating for decades finally reaches critical pressure and temperature. A thin shell, no more than a few meters thick, becomes the scene of runaway nuclear fusion. The reaction spreads in a flash, engulfing the star's surface. This is not a core explosion like a supernova, it's a surface detonation. But the energy released is still trillions of times more than Earth's annual output. Within seconds, the outer layers are blown off at speeds of thousands of kilometers per second. But this initial blast emits high-energy photons, X-rays and extreme ultraviolet radiation, that are completely invisible to the human eye. They are the first signals to reach our telescopes. NASA's Swift and NICER, orbiting in the void above Earth's atmosphere, will likely be the first to detect the change. These spacecraft will see a sudden surge in soft X-rays, a brief but unmistakable flare that signals ignition. Almost simultaneously, in the ultraviolet range, instruments aboard Hubble and other UV telescopes will pick up the shockwave moving outward. These emissions often precede the rise in visible light by hours, sometimes even a full day. This gives ground-based astronomers a narrow but thrilling window, we'll know the nova has begun before we can see it with our eyes. Then comes the visible light, and fast. Over the course of a single night, TCRB could rise from a faint magnitude 10, invisible to the naked eye, to magnitude 2 or even brighter, comparable to the stars in the Big Dipper or Vega and Lyra. This would make it easily visible even from cities, and a truly breathtaking spectacle from dark rural skies. Imagine looking up and seeing a new star in a well-known constellation, glowing fiercely from a position where nothing was visible the night before. The public reaction alone could rival past celestial events like the great comets or eclipses. Cameras will capture the light. Telescopes will track it in every filter. Spectrographs, instruments that split light into its component colors, will go into overdrive. We will see the nova's spectral lines split and broaden, revealing the velocity of the ejected gas. Hydrogen, helium, and possibly traces of heavier elements like carbon, nitrogen, and oxygen will shine in characteristic wavelengths. These spectral fingerprints will allow us to reconstruct the explosion, layer by layer. Meanwhile, in the infrared, the James Webb Space Telescope will be observing something even more intimate: the formation of dust. As the ejected gases cool, molecules begin to stick together. First simple compounds, like carbon monoxide, then silicates and carbon grains. Dust, the building blocks of planets and moons. JWST will peer into this post-eruption cocoon, capturing the chemistry of stellar ashes forming in real time. In the radio spectrum, massive arrays like ALMA and the Very Large Array, VLA, will scan for shockwaves as they interact with surrounding material. These observatories might detect synchrotron radiation, light emitted by electrons spiraling in magnetic fields, as magnetic forces amplify and twist in the aftermath. This radio light can continue for weeks or even months, tracing the journey of the nova's debris as it travels outward, possibly colliding with material from previous eruptions. Back on Earth, every photometric network, every backyard telescope, and every robotic observatory will be locked on the star. There will be live charts online, graphs showing minute-by-minute changes in brightness. Amateur astronomers will flood forums and social media with raw images and observations. It will be, in every sense, a global astronomical event. Schools will use it for lessons. News anchors will mention it between sports and weather. Even people with no prior interest in space will look up, see something unusual, and wonder. And for scientists, it will be an unprecedented opportunity. For the first time, a recurrent nova's eruption will be measured from start to finish with today's tools, capturing not only the explosion, but the buildup, peak, and decay with high-fidelity data. We'll track how the brightness changes across wavelengths, how quickly the temperature drops, how fast the gas expands, and whether the white dwarf's mass changed as a result. But what's more, we'll compare it to the past. We have data from 1866. We have much better data from 1946. And now, in the 2020s, we will complete the triptych. A 3-point record spanning over 150 years of cosmic time. From these 3 events, we will learn not only how TCRB erupts, but how it evolves. Is the cycle shortening? Is the energy increasing or decreasing? Is the mass of the white dwarf growing, and if so, how close is it to critical? The eruption might last several days at peak brightness before slowly fading, week by week, back into obscurity. But even as it dims in visible light, it will continue to shine in infrared and X-rays. The echoes of the blast, shock waves, molecular clouds, expanding shells, will linger for months or years. And they will be tracked, mapped, and modeled. This is what makes TCRB's impending eruption so different from any that have come before. It will not be a mysterious light in the sky noted in some observatory's logbook. It will be a comprehensively documented astrophysical event, captured at millisecond resolution, across the electromagnetic spectrum, with the combined intelligence of an entire planet's scientific instruments. We are about to witness a star die and live again, and this time, we won't miss a moment. For all the predictive models, historical comparisons, and real-time surveillance we've placed on T Coronae Borealis, the truth remains unsettlingly simple. It could still surprise us. Despite our sophisticated instruments and powerful simulations, the cosmos has a long history of defying expectations. And TCRB, a system teetering on the edge of explosion, holds more than enough secrets to catch us off guard. This is the uncomfortable beauty of transient astrophysical events. We understand the broad strokes. We can say with confidence what should happen. But the fine print, the details that define each eruption as unique, are often written only at the moment of ignition. TCRB's previous two eruptions, 1866 and 1946, were not identical. Subtle differences in brightness, speed of onset, and post-eruption behavior were recorded. So it's not a stretch to imagine that the third act in this stellar trilogy could veer from the script altogether. The most immediate question on everyone's mind is, could it erupt sooner than we expect? Absolutely. While 80 years is the rough recurrence interval, it's not an exact clock. The 1946 eruption came just 80 years after 1866, yes. But that doesn't mean the next must wait exactly 80 years. These cycles depend on how quickly the white dwarf accumulates enough mass to ignite fusion. If the red giant has increased its rate of mass loss in recent decades, if the accretion disk has become more efficient, or if environmental factors like magnetic field dynamics have changed the flow of gas, the nova could occur ahead of schedule. And recent observations, from infrared brightening to ultraviolet fluctuations, suggest this very possibility. The opposite is also true. It might delay. Just because all the warning signs are in place doesn't guarantee the final step. The pressure at the white dwarf's surface must cross a very specific threshold before ignition. If mass transfer suddenly slows or the accreted hydrogen becomes more diffuse than expected, the system could hover in this pre-eruptive state for years longer than anticipated. It might even fall quiet again, like a breath held in suspense. We've seen this kind of last-minute hesitation in other recurrent novae before, where a star flirts with eruption, then retreats into silence for a frustrating stretch of time. But beyond the when, is the bigger wildcard. What will the eruption actually look like? Could it be brighter? That too is possible. If the amount of hydrogen built up is larger than before, say, because of higher mass transfer or because the white dwarf's gravity has grown slightly stronger, the explosion could produce a greater energy release. The peak brightness might exceed magnitude 2, perhaps even approaching magnitude 1. That would make it one of the brightest stars in the sky, outshining most constellations, and drawing eyes to the heavens who've never before noticed the gentle curve of Coronae Borealis. It's also plausible that the nova could be dimmer than in previous cycles. If the ejected material is unusually dusty or if the explosion geometry is asymmetric, meaning it doesn't release energy evenly in all directions, we might see a softer, shorter peak. It could still be bright, still visible, but not as dazzling as some are hoping for. And this would raise fascinating questions about what's changed internally in the system, whether the white dwarf is evolving in unexpected ways or whether environmental conditions in its immediate surroundings have begun to interfere. Then there's the possibility of unusual post-eruption behavior. Could the brightness linger longer? Could there be secondary flares, smaller bursts of light following the main event, caused by unstable fallback of material? Could the star experience polar jets, shooting matter out in high-speed streams along its magnetic axis? All of these have been observed in other nova systems, and while TCRB hasn't shown them before, it doesn't mean it never will. In fact, there's a growing body of evidence that each nova in a recurrent system changes the environment for the next. The white dwarf loses some mass in the eruption, yes, but it also alters the density and structure of the space around it, leaving behind gas shells, shock waves, and debris. The new eruption must push through the remnants of its predecessor. If the 1946 shell is still nearby, even partially, the 2020's blast might interact with it, producing unexpected shock fronts or unusual light curves. This could generate emission lines in new wavelengths or a more complex brightness decay, unlike the smooth fades we've previously tracked. And then, there's the wild card of unknown physics. Could there be a brief gamma-ray flare? Could the eruption trigger neutrino emissions detectable by underground observatories? Could gravitational microlensing from interstellar matter slightly alter our view? These are speculative, yes, but not impossible. Every major nova observed in high detail has revealed some new behavior, some nuance that expands our models. TCRB, erupting in full view of 21st century technology, is almost guaranteed to teach us something we didn't anticipate. This is what makes the coming event so electrifying. It's not just that TCRB is going to erupt, it's that we don't know exactly how. The surprise is part of the thrill, and also part of the value. In unpredictability lies discovery. In chaos, clarity. There is also something deeply human in our anticipation of this eruption. We like predictability. We like calendars and countdowns. But the universe doesn't always cooperate. And TCRB, while following broad patterns, remains a free agent of the cosmos. It will erupt when it chooses, and in whatever way its internal physics dictate. Our job is to stay ready. To point our instruments, refine our models, and stay patient in the face of mystery. The surprise, when it comes, will not be unwelcome. It will be a reminder that even the most studied systems, even stars we think we know intimately, can still astonish us. There is a strange, almost poetic tension in watching T Coronae Borealis. Night after night, astronomers and hobbyists alike stare into the velvet black curve of Coronae Borealis, fixated on a single, faint point of light that, on the surface, appears as calm as any other star. But we know what lies beneath. We know what's coming. TCRB is not just a star anymore. It is a cosmic time bomb, ticking ever closer to ignition, its stillness a mask for the violence simmering inside. And in that tension, that unbroken quiet before the burst, lies one of the most profound metaphors in modern astrophysics. We are, in essence, watching a delayed explosion in slow motion. Every photon that TCRB sends toward us now is a whisper from a star on the verge. Its light is filled with secrets, temperature fluctuations, density waves, ultraviolet pulses, and infrared tremors that suggest movement in the unseen layers just beyond our reach. This isn't just a matter of observation. It's a kind of communion with deep time. Because what we're seeing, this delicate buildup, is a story nearly a century in the making. Every day the system persists without erupting, the pressure builds. Every hour that the accreted hydrogen doesn't ignite, it creeps closer to the threshold. And that's what makes it feel like a time bomb. Because unlike many celestial phenomena that are utterly random, TCRB gives us a window. A timeline. A sense that there is a fuse, even if we don't know its exact length. There's a visceral tension here, one that combines scientific anticipation with existential unease. It's not dangerous to Earth, of course. But emotionally, symbolically, it feels close. The idea that a star can sit silently for 8 decades, collecting the slow trickle of stolen mass, until one day it simply can't contain it anymore, that has echoes of things we understand as humans. Pressure. Suppression. Release. In many ways, TCRB is the astrophysical embodiment of repressed energy. The red giant feeds its partner not with generosity, but through gravitational submission. It loses parts of itself, layer by layer, to the gravity well of its companion. The white dwarf, in turn, accepts this gift not passively, but hungrily, compressing it, heating it, pushing it to a point where the laws of physics themselves will no longer allow equilibrium. When that point arrives, the system has no choice. The shell must detonate. And so we wait. Scientists often use the word, imminent, to describe its state now, but that word is slippery. It could mean tonight. It could mean next year. What matters is that the mechanisms are in motion. The bomb is armed. But this is no ordinary bomb. It doesn't destroy the star system, not yet. It doesn't rip apart spacetime like a black hole or flood the cosmos with gamma rays like a supernova. It releases, then resets. The system survives. It flares, then dims. The white dwarf loses some of the mass it spent decades collecting, but not all. Some mass remains. And after the light fades and the gas cools, the cycle begins again. And here's where the time bomb metaphor takes a darker turn, because one day, perhaps not during this eruption, perhaps not during the next, the system may reach a point of no return. If the white dwarf gains enough mass, if it crosses the Chandrasekhar limit, the maximum mass a white dwarf can support, then it won't erupt in another nova. It will collapse entirely. That will be a Type I supernova, a cataclysmic detonation that will tear the white dwarf apart in a moment of pure, unrestrained energy. Unlike the recurrent novae that simply flare and fade, a Type I supernova is a final act. No return. No rebuilding. No cycle. This casts every eruption in a new light. Is this the last one? Will the next be the end? Are we watching a stable rhythm, or the final flickers of a dying mechanism? It's a question without an answer, and that ambiguity only deepens the poetic resonance. We are watching something that is doomed, in the long-term sense, and yet it still pulses with life. Still erupts. Still returns. It's a metaphor for aging, for inevitable decay, and for resilience all at once. From the standpoint of science, this slow countdown is thrilling. We are building a timeline of stellar instability. We are mapping a detonation in advance, not reacting to it, as we often must with novae, but anticipating it, dissecting its prelude in exquisite detail. It's an opportunity to study not just a nova, but the conditions that lead to nova formation with unprecedented precision. And from that, we can extrapolate to other systems. We can apply what we learn here to supernova progenitors, to galactic chemical evolution, to stellar death on universal scales. But from the standpoint of the human spirit, there's something even more powerful. There is a kind of humility in watching a star prepare to explode. It reminds us that the universe operates on timescales far beyond our own, that cosmic violence can be both slow and sudden, predictable and chaotic. TCRB is a monument to that contradiction. A slow-brewing catastrophe. A quiet storm that has waited patiently for the right moment. There's a reason astronomers speak of this event not just in scientific terms, but in emotional language. We speak of waiting, of watching, of the return. Because something about this feels personal. Not in danger, but in intimacy. We've seen this star. We've tracked it. Some astronomers have spent their whole careers waiting for this one event. Generations of observers, passing the torch, building the data set, whispering to the next group. Watch this one. It's going to go. And still, it waits. The night it does erupt, whether in a blaze of expected glory or in a dazzling new form we didn't predict, will be a night of both triumph and silence. Triumph because science will have met the event with readiness, and silence because a process older than our species will have unfolded, not in our control, but in our gaze. Until then, the star ticks on. Quiet. Cold. Coiled. Waiting to blaze. Let us step into a what-if scenario, a realm of speculation grounded in real astrophysical theory, yet charged with the kind of drama that makes cosmic questions so mesmerizing. Suppose that one day, perhaps during the next eruption or perhaps 100,000 years from now, T Coronae Borealis does not follow the familiar pattern of flaring and fading. Suppose the shell of hydrogen ignites, but this time, it triggers something deeper, more catastrophic. Suppose the white dwarf has grown just massive enough to exceed its threshold, the Chandrasekhar limit, around 1.4 solar masses, and cannot support its own weight any longer. What happens next is no longer a recurrent nova. It is not a surface flare. It is not survivable. It is a Type I supernova, one of the most powerful, destructive, and illuminating events in the universe. A detonation that utterly obliterates the white dwarf, leaving nothing behind but an expanding shell of radioactive ash and a blinding beacon of light visible across galaxies. No more cycles. No more returns. Just one final act of stellar suicide so complete that it vaporizes the very core of its former self. This is not idle fantasy. The threat of TCRB going supernova is a real, albeit distant, possibility. Many recurrent novae systems are believed to be candidates for future Type I supernovae, and TCRB fits several key criteria. A white dwarf steadily accreting mass from a red giant. Regular nova eruptions that suggest an efficient accretion process. And potentially, a white dwarf already quite massive, inching ever closer to its final limit. If it happened, if T Coronae Borealis exploded as a Type I supernova, what would we see? First, the magnitude of the explosion would be far beyond anything witnessed from a recurrent nova. At its brightest, TCRB in a nova phase reaches magnitude 2, easily visible to the naked eye, but modest compared to the stars that define our constellations. A Type I supernova, however, could reach magnitude -5 to -6, rivaling or even surpassing Venus in brilliance. It would become one of the brightest objects in the night sky, outshining every star, and possibly even casting shadows at night under dark skies. This luminous beacon would rise over the Coronae Borealis constellation not as a point, but as a new star, blazing white with intense light. Observers from Earth would be able to see it for weeks or even months, slowly dimming but never quite fading quickly. It would make headlines worldwide, trigger emergency telescope sessions, and even confuse people unfamiliar with celestial phenomena. Social media would explode with photos and videos of a new light in the sky that wasn't there before. But brightness is only one part of the story. More critically, the physics of a Type I supernova would unfold in spectacular detail. The explosion begins not with fusion on the surface, but with the collapse of the white dwarf's core. As the mass surpasses the Chandrasekhar limit, gravity overwhelms the electron degeneracy pressure that had been supporting the white dwarf's structure. In a fraction of a second, the star's carbon and oxygen-rich interior ignites in a runaway thermonuclear reaction. This reaction doesn't stop at the surface. It consumes the star from the inside out. No remnant is left behind, no neutron star, no black hole. Instead, the entire white dwarf is torn apart in a titanic release of energy, roughly 10 billion trillion joules, or about the energy output of the Sun over 10 billion years, released in seconds. The debris flies outward at speeds approaching 5% to 10% the speed of light, scattering radioactive elements like nickel-56, which decays into cobalt and then iron, powering the supernova's glow. Telescopes would capture a light curve unlike anything seen from TCRB before. Instead of peaking in a day and fading over a week or two, as in a nova, a Type I supernova would rise over about 17 to 20 days, reach maximum brightness, and then slowly decay over the course of months. Spectroscopy would reveal broad absorption lines from the rapidly expanding ejecta. The star's spectrum would be rich in iron group elements, especially those produced during the detonation. Unlike core collapse supernovae, from massive stars, Type I supernovae have no hydrogen in their spectra, which would confirm to scientists that this was not the death of a giant star, but of a degenerate white dwarf. The presence of silicon absorption lines around 615 nanometers would nail down the classification as a Type I. And unlike the relatively mild ejection of a nova, this event would leave no central star. TCRB would vanish, replaced forever by a faint, expanding nebula of gas and dust. From Earth's perspective, aside from the breathtaking visual spectacle, there would be no danger. TCRB lies around 2,600 light-years away, too far to cause biological harm through radiation or atmospheric effects. The high-energy radiation from a Type I supernova diminishes rapidly with distance, and Earth's magnetic field and atmosphere would shield us from anything measurable. But what we could detect, and study for generations, is the neutrino emission, X-ray bursts, and possibly gravitational waves produced during the collapse. It would be an unmatched scientific opportunity. This explosion would immediately join the ranks of the closest Type I supernovae ever recorded. Currently, the most famous nearby example is SN 1572, Tycho's supernova, which also reached visible magnitude during its peak and was studied with the naked eye in the 16th century. But unlike Tycho, we would observe this supernova with 21st century instruments, from its initial flicker to its afterglow years later. We could capture the chemical evolution of its remnant, map the structure of the ejected material, and measure the expansion rate of its shell with millimeter precision. For the broader field of astrophysics, this would be a treasure trove. Type I supernovae are used as standard candles in cosmology, reliable distance markers that help discover the accelerating expansion of the universe and the existence of dark energy. But despite their importance, we still have unanswered questions. What triggers them exactly? What is the exact pre-supernova mass transfer dynamic? Do all of them arise from single-degenerate systems like TCRB, or do double-degenerate, white dwarf plus white dwarf, systems dominate? If TCRB were to go supernova, we would witness the entire life cycle, from slow mass transfer and recurrent novae, through thermonuclear instability, to final collapse. It would be the most complete observational dataset ever collected on a Type I progenitor. The entire sequence would become a reference model for future research. And beyond the science, there's the human element, the profound emotional and philosophical resonance of watching a star die in real time. Imagine the moment it happens, the announcement echoing across scientific institutions, the public invited to witness history unfolding in the night sky, millions of people around the globe lifting their eyes to see a once-and-forever burst of stellar death. It would provoke awe, fear, wonder. Artists would paint it. Poets would write of it. Children would be inspired to study the stars. And somewhere, in the quiet curve of Coronae Borealis, the ancient blaze would burn one last time, not as a flare to be repeated, but as a final signature carved into the cosmos. The red giant companion would be left stunned, adrift, its partner gone in a breath of thermonuclear fire. The binary would be no more. T Coronae Borealis, the blaze star, would become a memory, recorded forever in archives, light curves, spectra, and stories. And yet, that story, terrifying and final as it may sound, would be one of creation as much as destruction. The iron released would enrich interstellar space. The dust formed would seed new planetary systems. The energy spread across space would ripple through the galaxy, stirring gas clouds, triggering star formation, or simply becoming another echo in the universe's deep silence. In the aftermath of destruction, the universe begins again. So we watch. We wait. And in the back of our minds, we carry this possibility like a silent secret. The blaze we await may not be a rehearsal. It might be the finale. And we'll be there to see it. The future of monitoring T Coronae Borealis stretches far beyond the anticipated flash of its next eruption. Whether it erupts tomorrow, next year, or surprises us decades from now, the attention it commands won't fade afterward. On the contrary, what happens after the eruption, and how we prepare for the one after that, may become one of the greatest case studies in long-term astrophysical monitoring. The star has already captured the attention of astronomers across generations. But as we move deeper into the 21st century, the methods by which we observe, predict, and understand this volatile system are set to evolve radically. Gone are the days when astronomers relied solely on visual estimates through eyepieces, penciling in a nova's appearance on the night's logbook. T Coronae Borealis is now being tracked in near-continuous cycles by automated, AI-powered sky surveys, remote sensing satellites, infrared instruments, ultraviolet telescopes, and radio observatories. And as the technology surrounding it becomes more sophisticated, our ability to catch the smallest pre-eruption changes and predict them will grow exponentially. The next few decades of observing TCRB are likely to be revolutionary, not just evolutionary. Artificial intelligence is already beginning to play a major role in astronomy, and it will be indispensable in systems like this. AI models trained on massive databases of transient stellar phenomena are being used to sift through the endless flow of sky survey data, identifying outbursts, subtle brightness shifts, spectral changes, and other signals that might otherwise go unnoticed by the human eye. These machine learning models can flag precursors to nova eruptions, compare behaviors across different known recurrent novae, and even simulate likely eruption profiles based on historical and current conditions. In essence, we're teaching machines to watch the stars for us, not just passively, but intelligently. Over the next 2 to 3 decades, instruments such as the Vera C. Rubin Observatory, with its Large Synoptic Survey Telescope, LSST, will be critical. This next-generation survey telescope is designed to scan the entire visible sky every few nights, capturing deep, wide-field images that will track changes in TCRB with exquisite precision. LSST will not only catch the eruption when it happens, but it will also record the build-up, the immediate aftermath, and every subtle flicker that precedes and follows. The dataset it will generate could help us refine eruption timing estimates for every recurrent nova, not just TCRB. But ground-based telescopes won't be alone. In space, NASA, ESA, and other agencies are preparing a fleet of observatories that will be sensitive to every wavelength TCRB can emit. The James Webb Space Telescope will provide deep infrared analysis, while future ultraviolet missions, possibly successors to the aging Hubble, will watch the high-energy light that signifies shock waves and post-eruption cooling. And if the eruption results in interesting dust formations or ejecta structures, even telescopes like the Nancy Grace Roman Space Telescope, formerly WFIRST, could be directed to examine the expanding shell over time. Meanwhile, X-ray and gamma-ray observatories like Athena, or proposed missions like Lynx, will allow scientists to monitor the extreme conditions near the white dwarf's surface in the minutes and hours after the next blast. These instruments may detect short bursts of high-energy photons that would otherwise be missed from Earth. They'll help answer some of the most urgent questions. How exactly does fusion ignite? What happens in the first seconds? Can we measure the mass ejection rate more precisely? And beyond the eruption itself, the long-term fate of the system is an equally important scientific goal. Once the next nova occurs, we'll be watching with new urgency for evidence of mass gain, whether the white dwarf is increasing in mass over time, inching towards supernova status. Over decades, this will be tracked by measuring the frequency, brightness, and decay rates of each future nova event. Astronomers will compare eruption intervals, post-eruption brightness decay curves, and total energy output to determine whether the white dwarf is gaining mass faster than it loses it. Here, too, AI will play an essential role. Predictive models based on recurrent novae will become real-time simulators, adjusted constantly as new data flows in. Observatories around the world will feed raw observations into cloud-based networks that aggregate, analyze, and predict nova behavior faster than ever before. In this future, astronomers may receive alerts not only that an eruption has begun, but that an eruption is about to begin, within a predicted margin of error. The starlight will be analyzed not just by experts, but by automated assistants trained to recognize the physics of stars in their final throes. Even citizen scientists will likely play a growing role. Platforms like the American Association of Variable Star Observers, AVSO, already include TCRB as a priority object. Amateur astronomers equipped with small telescopes and sensitive CCD cameras are contributing valuable data daily. In the future, apps and network telescopes might allow amateur observers to plug into a global monitoring network, where their observations are verified, compared, and merged into international light curves used by professionals. TCRB's story is one in which the boundary between amateur and professional has become increasingly blurred, a trend that will only accelerate. And yet, even as our tools grow smarter, and our models more precise, we will still wrestle with uncertainty. Because for all our progress, stellar systems remain complex, chaotic, and at times deeply unpredictable. AI may one day reduce the timing of nova eruptions to a matter of hours, but it will never fully eliminate the possibility of surprises. TCRB, like so many astrophysical systems, is governed not just by rules but by interactions, turbulence in gas, magnetic fluctuations, instabilities that emerge from complexity itself. That's part of why we'll keep watching. Not just for the data, but for the awe. For the knowledge that we are witnessing a moment in stellar time, a phase transition in the life of a binary system, and perhaps, eventually, the death of one of its members. Each future eruption will be more than just an event. It will be a marker, a data point in a story centuries long, stretching from the dusty observatories of the 1800s to the cloud-powered observatories of the 2100s. And maybe, someday, generations from now, when the system erupts again in the 2100s or beyond, astronomers will look back not only at the eruption itself, but at the decades of monitoring that preceded and followed it, a chain of observation made possible by machine learning, global coordination, and a quiet, unwavering human fascination with things that flicker on the edge of eternity. We are no longer just watching T Coronae Borealis. We are learning to understand it. In the quiet curve of the northern sky, nestled in the delicate horseshoe of Coronae Borealis, a single star holds us all in suspense. It does not roar or rage. It does not shimmer with the colors of a dying giant. It sits there, modest, faint, nearly invisible to the naked eye, an unassuming pinprick of light. But beneath that calm surface, forces are gathering. Layers of gas spiral down through space. Pressure mounts on an ancient core. Temperatures climb beyond anything we can imagine. And the clock ticks. It's not often that humanity finds itself collectively waiting for a star to explode, not with fear, but with awe. We are not hiding from it, we are looking for it. We point our telescopes at it every night. We refresh satellite data. We check magnitude reports. We sift through infrared noise and compare patterns across decades. And yet, as advanced as we are, armed with machine learning, space telescopes, and sky monitoring networks that span the globe, we still don't know when. Not exactly. This is what it means to live in a universe where some clocks have no hands, where time is written not in hours or days but in pressure thresholds and fusion triggers. We know that T Coronae Borealis will erupt again. We know it because it has done so before. In 1866, it stunned astronomers. In 1946, it rose again, as predicted, brighter, faster, fiercer. Now, the signs are all there: ultraviolet increases, temperature shifts, irregular pulsations. Something is happening beneath that surface. And so we wait. Not passively, but attentively. Not with idle curiosity, but with a sense of shared anticipation, like an audience waiting for the curtain to rise on a performance rehearsed across lifetimes. It's rare that science and poetry intersect so closely, but here they do. Because this star, the Blaze star, is not just an object of study. It's a story. A celestial drama with a rhythm that spans generations. A whisper in the sky that once every human lifetime speaks in fire. And when it does, the world will notice. Skywatchers will lift their eyes and see a star where there was none. It will bloom from invisibility to brilliance in a matter of hours, turning a faint speck into a lantern that outshines constellations. People will post photos, ask questions, rush outside to see it for themselves. The star charts will change. The maps will be redrawn. For a short while, Coronae Borealis will wear a jewel it only wears once in a lifetime, and we, the lucky ones, will be here to witness it. But that day is not today. Not yet. The sky remains quiet. The blaze has not begun. We are left in the waiting, between what has already happened and what is surely coming. And that waiting, that space between the known and the imminent, is where something deeper happens: connection. Across telescopes and time zones, across generations of scientists and stargazers, we are united by the act of looking up, not in fear or despair, but in wonder. This is the essence of astronomy. To know that something vast and beautiful is about to happen, and to choose to watch for it. So we watch. T Coronae Borealis is still gathering strength. The red giant still feeds its companion. The white dwarf still accepts its burden. And somewhere deep inside, beneath a crust of atomic density, a fuse slowly burns. One day, perhaps tomorrow, perhaps years from now, the blaze will return. And when it does, the universe will speak. And we'll be here to listen. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.